on October 21st, 2025. Something changed. Independent astronomers comparing live tracking data to NASA's official predictions noticed the impossible. 3IATLAS wasn't where it was supposed to be. Not by a few kilometers, not by 1,000, by over 1 million kilometers, and growing wider with every passing hour. The interstellar visitor that's been dominating headlines since July had done something no natural comet should be able to do. It accelerated ahead of its predicted gravitational path. 8 days later, it vanished behind the sun at the exact moment its velocity peaked, hidden from every telescope on Earth during the single, most energy-efficient window for any spacecraft to execute a course change. Now, as it approaches perihelion on October 29th, the object will remain invisible, shielded by solar glare, performing whatever it came here to do in complete darkness. When it reemerges in early November, we'll know if the deviation was an error in our calculations, or if something out there just made a deliberate move. The next 2 months will either confirm we're watching the most unusual comet in recorded history, or prove that Avi Loeb's warnings about alien technology weren't speculation at all. If you're just as fascinated by what's unfolding up there as I am, hit that like button and subscribe so you don't miss what happens next. And drop a comment telling me where you're listening from, what time it is there right now, and whether you think we're looking at a comet or something far more intentional. And if you want to help this community grow, share this video and hit that new hype button below. Thank you so much for your support. The trajectory anomaly. Active maneuvering claims the data came in quietly at first. October 21st, 2025, 0012, Coordinated Universal Time. Full of independent trackers running routine sky surveys noticed something odd when cross-referencing their observations against the Jet Propulsion Laboratory's Horizon system. 3IATLAS, the interstellar object that had been behaving relatively predictably since its July discovery, had drifted off course. Not the subtle drift you'd expect from measurement error or outgassing pressure. This was different. The object appeared ahead of where gravity alone should have placed it. Let's establish what that means. When you track any celestial body, whether it's a satellite, asteroid, or comet, you're essentially watching gravity's invisible hand guide it through space. The JPL Horizon system is one of the most sophisticated astronomical tools we have. It calculates where objects should be, based on gravitational forces from the sun, planets, even the subtle tug from Jupiter's mass millions of kilometers away. These predictions are extraordinarily accurate. When Mars rovers land, when spacecraft perform flybys, when we track near-Earth asteroids, Horizons tells us where to look within margins measured in meters, not kilometers on that October morning. Horizons predicted 3IATLAS would be at right ascension 13 hours, 46 minutes, 57.51 seconds. Declination, -8 degrees, 15 arc minutes, 20.0 arc seconds. That's where NASA said the object would appear in the sky, but the observed data told a different story. Multiple independent tracking stations, cross-referencing their measurements, found the object at right ascension 13 hours, 47 minutes, 54.3 seconds, declination -8 degrees, 21 arc minutes. For those who don't speak astronomical coordinates, let me translate. That's not a small discrepancy at the distance 3IATLAS was traveling, roughly 2.38 astronomical units from Earth. That angular offset translated to approximately 1.1 million kilometers of lateral displacement. Now, here's where it gets genuinely strange. When tracking systems show a mismatch between prediction and observation, the error typically appears in a specific direction. If your orbital data is outdated, the object appears behind where you expected it. Think of it like trying to hit a moving target with old information. You're always shooting where it was, not where it is. Orbital mechanics has predictable patterns. Comets accelerate as they approach the Sun, decelerate as they move away. Outgassing can create small, non-gravitational forces, tiny jets of vapor pushing the object slightly off course. All of this is well understood, documented in thousands of comet observations going back decades. But 3IATLAS appeared ahead of its predicted position, not behind. Ahead. That breaks the usual pattern completely. When an object shows up ahead of gravitational predictions, it suggests something is pushing it forward, adding energy to its motion. For a comet, that would require asymmetric outgassing pointed in exactly the right direction to accelerate the object along its trajectory. Possible, certainly. Comets can be unpredictable, but the timing here raises questions that are harder to dismiss. The group that first documented this deviation publicly goes by the name Earth Exists. They're not NASA. They're not affiliated with any major observatory. They're part of a growing network of citizen astronomers who've taken it upon themselves to track 3IATLAS independently, using publicly available telescope data and sky survey archives. Some might dismiss amateur, but these aren't kids with backyard telescopes. These are individuals with access to serious equipment, people who understand astrometry, orbital mechanics, photometry. They've been cross-checking their findings against multiple data sources, comparing images from different observatories, running their own calculations. According to their analysis, released on October 22nd, the positional offset wasn't static. It was growing 19 hours after the initial October 21st observation. They ran another positional analysis. The divergence had increased. They calculated the rate at roughly 0.23 arc minutes per hour, which at that distance translates to a lateral velocity change of nearly 4 kilometers per second. That's not drift. That's not measurement noise. That's a sustained deviation from the expected gravitational path. Let's put 4 kilometers per second in perspective. That's roughly 14,400 kilometers per hour. For reference, the fastest human-made spacecraft, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at perihelion, but that's falling toward the Sun with massive gravitational assist. We're talking about lateral motion here, perpendicular to the main trajectory. A velocity change like that requires force. For a comet, that force would come from outgassing jets of sublimating ice turning to vapor and pushing against the nucleus. But here's the problem. When comets outgas strongly enough to create measurable trajectory changes, they get bright, very bright. You see massive plumes, extended tails, dramatic increases in magnitude. 3IATLAS was doing the opposite. JPL had predicted an apparent magnitude near 14.8. That's already faint, requiring decent amateur telescopes to observe. But actual readings showed the object at magnitude 15.1, about 26% dimmer than expected. This is backwards. If outgassing was strong enough to push the object 1 million kilometers off course, we should be seeing the brightest interstellar comet in history. Instead, it's dimmer than predicted, even though the James Webb Space Telescope confirmed it's losing about 25 kgs of water every second. So, we have an object that's deviating from its predicted path in a way that suggests forward thrust, while simultaneously appearing dimmer than it should despite confirmed active outgassing. These facts don't reconcile easily with standard comet behavior. They create a tension that astronomers are trying to resolve with increasingly creative explanations. Some have suggested the nucleus is rotating in a way that hides the main active regions from Earth's view. Possible, but convenient. Others point to the composition anomalies discovered by the Keck Observatory in August, the unusual nickel emissions without corresponding iron, the remarkably low water content for an active comet. Maybe this object's chemistry is so different from solar system comets that it behaves in ways we simply don't have models for. Also possible, interstellar comets are rare, We've only studied 3. Perhaps our assumptions about how they should behave are just wrong. But then there's the third explanation, the one that most mainstream astronomers won't touch publicly, but discuss privately. What if the deviation isn't random? What if something about 3IATLAS is capable of adjusting its trajectory, not through natural outgassing that happens to be pointed in a convenient direction, but through something more deliberate? Avi Loeb has been saying this for months. Ranking the object at 4 out of 10 on his scale of potential technological origins, the accumulation of anomalies, he argues, pushes the probability of natural explanations below comfortable thresholds. Each oddity alone can be explained. All of them together start to look like a pattern. The tracking community isn't unified on this. Some groups have tried to reproduce the Earth exists findings and claim they can't confirm the same magnitude of deviation. Others say their data show similar trends, but attribute it to outdated orbital elements in the JPL database. Orbital elements are the mathematical parameters that define an object's path through space. They get refined as more observations come in. Maybe JPL's last update was October 10th, and by October 21st, those elements were stale enough to cause prediction errors. Except here's the thing. JPL updates orbital elements for near-Earth objects and significant comets regularly, especially for something as high-profile as 3IATLAS. The idea that they'd let the data go stale by 11 days during the approach to perihelion seems unlikely. This is exactly the period when tracking would be most critical, when observatories worldwide are pointing instruments at this object, when NASA has coordinated observations from Mars orbiters, the Hubble Space Telescope, James Webb, and ground-based facilities across multiple continents. David Soreta, another independent researcher, added fuel to this particular fire on October 20th. He was reviewing images from NASA's LASCO C3 coronagraph, a solar telescope designed to observe the sun's corona by blocking the bright disk. LASCO captures images of the space around the sun, and comets occasionally pass through its field of view. Soreta documented something unusual in multiple frames. 3IATLAS appeared to display geometric light structures, not the diffuse circular glow you'd expect from a comet's coma, but sharp-edged patterns. In one image, the glow formed what he described as a cross like plasma geometry before the object disappeared from the next several frames, then reappeared, then vanished again. Now, LASCO images are notoriously difficult to interpret. You're looking at extremely faint objects through a coronagraph designed for solar observation, not deep space imaging. Artifacts are common. Image processing can create false patterns. Cosmic rays hitting the detector create bright spots. Spacecraft telemetry errors produce gaps in the data. Skeptics immediately pointed to these factors. What Soreta called geometry, they called noise. But here's what made the claim harder to dismiss. Earth Exists had done their own analysis of 3IATLAS using single-image enhancement techniques. No stacking, no processing beyond basic contrast adjustment. They saw similar patterns: green outer edges, blue core, pink zones, arranged in distinct geometric sections. They compared this to reference stars in the same field of view, Spica and Comet C, 2025 R2 Swan. Those sources appeared perfectly circular and in stellar symmetry. 3IATLAS didn't. The coloration matches. Spectroscopic analysis done by the Keck Observatory back in August: cyanogen, ionized nickel, hydrogen plasma. Each element emits light at specific wavelengths, creating distinct colors when you split the spectrum. But typically, those emissions mix into a diffuse glow. The claim here is that they're spatially separated into defined zones, as if the plasma around the object is somehow structured rather than random. That would be consistent with controlled magnetic fields organizing charged particles, the kind of behavior you'd see around a fusion reactor or a magnetized spacecraft. Not a ball of dirty ice. I want to be careful here. Extraordinary claims require extraordinary evidence, And what we have right now are provocative observations from non-institutional sources. That doesn't make them wrong. Citizen science has a strong track record. Amateur astronomers discover comets, track asteroids, even spot exoplanet transits. But it does mean the findings need independent verification from facilities with calibrated instruments and peer-reviewed methodologies. So far, major observatories haven't released data confirming or denying these specific geometric pattern claims. What we do have is silence, or more accurately, delayed releases. The Mars Reconnaissance Orbiter's high-rise camera was supposed to image 3IATLAS during its closest approach to Mars on October 3rd. Those images, with a resolution of about 30 kilometers per pixel, could potentially show surface structure details, maybe even confirm whether the brightness distribution matches natural outgassing or something more organized. As of October 23rd, those images haven't been publicly released. NASA cited the government shutdown as a reason for delays. But that explanation sits uneasily with many observers. This is arguably the most significant interstellar object to pass through the inner solar system in recorded history, and data is being held back during the most critical observation window. Maybe there's nothing unusual in those images. Maybe HiRISE saw exactly what you'd expect, a fuzzy blob with a tail, and NASA just hasn't gotten around to processing and releasing the files. Or maybe what they saw requires careful analysis, consultation, verification before going public. We don't know. And that uncertainty creates space for speculation to flourish. What we do know, what's documented and verifiable, is that multiple independent groups using different methods claim 3IATLAS is not following its predicted gravitational path. The deviations they're measuring, if accurate, would require forces beyond simple solar radiation pressure or symmetric outgassing. Those forces would need to be directed, sustained, and significantly more powerful than what we typically observe from comets of similar size and activity level. And all of this is happening during the final week before perihelion, the week when the object passes behind the Sun and becomes completely unobservable from Earth. October 29th, 2025, 1.356 astronomical units from the Sun, hidden in the glare. If you were designing a trajectory to execute a course change without being watched, you couldn't pick a better moment. The Oberth effect, named after Hermann Oberth, states that the most energy-efficient time for a spacecraft to burn its engines is at the point of highest velocity, typically at perihelion. A small thrust applied when you're moving fast produces a much larger change in orbital energy than the same thrust applied when you're moving slowly. So here we sit an object with a growing positional offset, geometric light patterns that may or may not be real, a dimming trend that contradicts its confirmed activity, and in 7 days from that October 21st observation, it disappears behind the Sun at the exact moment any intelligence system would choose to make it its move. The math works out a little too perfectly. The timing feels a little too convenient, and the lack of clear explanations from official sources creates a vacuum that speculation rushes to fill. By November 3rd, 3IATLAS will reemerge. We'll see if the offset persists, increases, or vanishes. We'll know if October 29th was just another perihelion passage, or if something used those 8 hidden days to adjust its course. Until then, we're left with data that doesn't quite fit, observations that don't quite align, and a growing sense that the universe might be about to remind us how little we actually understand. SETI Protocols. Update, October 16th, 2025. The Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence. Hasn't changed much since 1989. That's the formal document endorsed by 6 international space and astronomy organizations that outlines what scientists should do if they detect a signal from an alien civilization. Verify it independently. Inform the Secretary General of the United Nations. Share data openly. And don't send a reply without international consultation. These principles guided SETI research for over 3 decades, with only minor updates in 2010 to streamline language and clarify procedures. On October 16, 2025, the International Academy of Astronautics SETI Committee published a comprehensive revision, not minor tweaks, a complete overhaul, expanding scope, updating protocols for modern technology, and adding new requirements that didn't exist in previous versions. The timing. Released during the exact period when 3IATLAS is generating maximum public interest and scientific debate, has not escaped notice. The revised protocols were years in development. A task group formed in 2022 to examine how SETI should adapt to changing information environments, expanded search methodologies, and increased international participation. They presented a draft at the International Astronomical Congress in Milan in 2024. Gathered feedback, refined the document, and brought it to final vote at the IAC in Sydney in late September 2025. The October 16th publication represents formal release after that vote, with full adoption expected before year's end. But perception matters as much as reality in public discourse. To casual observers, SETI, updating its first contact protocols right when an anomalous interstellar object is approaching perihelion, looks like preparation for an imminent event. Conspiracy communities immediately connected the dots. SETI knows something. They're getting ready. The protocols needed updating now, not next year, because something might happen in the coming months that requires those new frameworks. The more mundane explanation is bureaucratic timing. International committee work moves slowly. The September IAC meeting in Sydney was the scheduled venue for voting on the revised document regardless of what 3IATLAS was doing. October publication follows standard academic practice of releasing papers shortly after conference presentations. The correlation with 3IATLAS's perihelion is coincidence, not coordination, except the document itself undermines that benign interpretation. The preamble explicitly mentions artificial intelligence, social media, and political chaos as factors shaping how detection announcements will unfold. It acknowledges that misinformation spreads faster than verified, that state and non-state actors might manipulate discovery claims for political advantage, that protecting researchers from harassment has become necessary. These aren't abstract fact concerns. They're responses to the current information environment where 3IATLAS discussions already demonstrate every problem the protocols aim to address. The new framework expands beyond radio signals. Previous versions focused almost entirely on electromagnetic transmissions. The classic SETI paradigm of listening for intentional broadcasts from distant civilizations. The 2025 revision includes technosignatures of any kind laser pulses, waste heat from megastructures, chemical biosignatures in exoplanet atmospheres, physical artifacts. That last category is new and significant. Physical artifacts mean objects like 3IATLAS. The protocols now explicitly cover scenarios where detection isn't a signal, but a thing. A manufactured object encountered directly. Principle number 7 is the most discussed change. It states clearly that, pending international consultation, no reply should be sent to a confirmed detection. Previous versions suggested consultation, but were vague on enforcing it. The new language is categorical: do not reply. Consult first. The consultation must go through the United Nations Committee on the Peaceful Uses of Outer Space, or other broadly representative international bodies. Single governments, institutions, or individuals cannot unilaterally speak for humanity. This represents a major shift in authority structure. Under old protocols, whoever detected a signal had significant discretion in how to respond. They were expected to consult, but not legally bound. The revised protocols create stronger normative pressure against unilateral action. If you detect something and reply without UN involvement, you're violating internationally recognized scientific standards. That's not legal enforcement. but it's reputational and professional enforcement, which can be equally powerful in academic and governmental contexts. Principle 8 addresses ethics and law, requiring consideration of potential impacts on human society, protection of discoverers from harassment, and adherence to legal frameworks governing space activities. This principle didn't exist in previous versions. Its inclusion acknowledges that detection won't be purely scientific. It will be political, social, and potentially dangerous for the people involved. Scientists who discover extraterrestrial intelligence might face death threats, worship, government pressure, media harassment, or worse. The protocols now formally recognize that risk and call for protective measures. The document also establishes a post-detection subcommittee within the IAA SETI committee. This standing group will assist and advise if detection occurs, offering expertise in interpretation, communication strategy, and managing the broader implications. Having that structure in place before detection means response isn't improvised. There's institutional memory, prepared procedures, designated experts. It's the difference between chaos and coordination. One subtle but important change involves data archiving. The new protocols require that evidence be stored in multiple geographic locations using tamper-proof records. Blockchain gets mentioned by name. The concern is data manipulation, either by discoverers who might fabricate evidence or by external actors who might try to suppress or alter genuine findings. Distributing encrypted, time-stamped copies of raw data across multiple secure repositories makes manipulation effectively impossible. Anyone can verify the original data against the archived copies. This level of data security wasn't necessary in 1989. Back then, the threat model was simpler. You worried about false positives, instrumental errors, misidentification of natural phenomena as artificial signals. You didn't worry about deepfakes, AI-generated false data, coordinated misinformation campaigns, or governments suppressing discoveries. The Internet changed everything. The new protocols reflect that reality. Another addition is frequency protection. If detection occurs via electromagnetic transmission, the revised protocols call for petitioning the International Telecommunication Union to protect the relevant frequency band from interference. This gives a legal mechanism for preventing terrestrial broadcasts that might jam or overwhelm the signal. It's a practical measure that also signals seriousness. You don't allocate international radio spectrum protection unless you're treating the detection as real and important. The community consultation process that shaped these revisions is noteworthy. The task group didn't just work internally. They used surveys, workshops, and engaged early career SETI researchers who will inherit these protocols. They even used ChatGPT for analyzing feedback, a detail mentioned explicitly in the paper. That's remarkable transparency about methodology, but also recognition that AI is now integral to the scientific process. If you're writing protocols for detecting alien intelligence, you can't ignore that human intelligence is already augmented by artificial systems. Critics have pointed out that protocols, however well written, don't have enforcement mechanism. SETI is a scientific community, not a government. The Declaration of Principles is voluntary. Signatories agree to follow them. But there's no penalty for violation beyond reputational damage if a rogue researcher or nation-state detects a signal and replies without consultation. The protocols can't stop them. They can only create social and professional pressure against such action. But that pressure matters. Science operates on reputation. Violating widely accepted ethical standards ends careers, damages institutions, isolates violators from collaborative networks. Most scientists care deeply about their professional standing. The revised protocols leverage that to create incentive structures favoring responsible behavior, even without legal force. The timing question persists. Why finalize and publish now? The task group's work began in 2022, before 3IATLAS existed. The Milan draft in 2024 predated most of the object's anomalies being widely known. The Sydney vote in September happened weeks before perihelion. At each stage, the process was following its own timeline, independent of interstellar visitors. Yet the final publication in mid-October, as global attention focuses on a potentially artificial object passing through our solar system, creates an unavoidable perception of connection. Maybe that perception is useful. If 3IATLAS turns out to be natural, the protocol update still serves future preparedness. But if observations in November and December reveal something that demands invoking these protocols, having them freshly updated and publicly available ensures everyone knows the procedures. There's no ambiguity about what should happen next. The international community agreed on the framework just weeks before it might be needed. Skeptics argue this is projection, reading intent into coincidence. The protocols were getting updated regardless. Publication timing followed academic convention. 3IATLAS being interesting during the same period doesn't imply causation. Scientists working on the revision weren't coordinating with astronomers tracking the object. These are separate communities with separate workflows that happen to overlap in time. Yet institutions talk to each other. The IAU SETI committee includes members who are aware of 3IATLAS. Michael Garrett, lead author on the revised protocols, works at institutions engaged in astronomical observation. Catherine Denning, another author, specializes in anthropological aspects of contact scenarios. These aren't people operating in information vacuums. They knew about the object. They knew about the anomalies. They knew that perihelion was approaching when they finalized the document. Whether that knowledge consciously influenced timing or not, the result is the same. Humanity enters the 3IATLAS post-perihelion observation period with updated, comprehensive protocols for responding to detection of extraterrestrial intelligence. If those protocols are needed, they're ready. If they're not needed, they still represent the most thoughtful framework ever developed for one of the most consequential scenarios we can imagine. The document includes something previous versions lack, a clear statement about when to use these protocols. They apply when evidence indicates intentional transmission or construction by non-human intelligence, not just any anomaly, not natural phenomena that's hard to explain. Evidence of intentionality, design, purpose, that's the threshold. Below it, you're doing interesting science. Above it, you're in contact scenario territory where these protocols activate. 3IATLAS sits on that threshold. The 8 anomalies suggest something unusual but don't definitively prove intent. If post-perihelion observations reveal trajectory changes inconsistent with natural forces, if we detect radio transmissions, if secondary objects separate and navigate independently, then intentionality becomes hard to deny. At that point, these protocols aren't theoretical. They're operational instructions for managing the most important discovery in human history. The revised protocols won't prevent chaos if that scenario unfolds. But they provide structure, they designate responsibilities, they establish communication channels, they protect researchers and data integrity. They ensure international involvement rather than unilateral action in a situation where everything will be unprecedented. And many things will go wrong. Having any framework is better than improvising completely. SETI researchers have waited decades for a detection. Most assumed it would be a radio signal from a distant star, light years away, allowing time for careful response without immediate consequences. 3IATLAS, if it is a detection, is very different. It's here, it's close, it's moving through our planetary system right now. Response time scales are weeks, not years. The luxury of slow deliberation doesn't exist. That urgency might explain why the protocols emphasize immediate steps. They verify independently, secure the data, inform the Secretary General. These aren't long-term strategic recommendations. They're acute-phase crisis management. Do these things first within hours or days to establish facts, and prevent misinformation from dominating the narrative. Longer-term responses can follow once immediate stabilization occurs. October 16th, 2025. The day SETI updated its playbook for contact. 13 days before 3IATLAS reaches perihelion. 18 days before it reemerges from behind the Sun for post-perihelion observations. The protocols are published, voted on, ready for implementation. Whether they'll be needed is a question for November and December to answer, but their availability, freshly revised and internationally endorsed right when they might matter most, is either extraordinary foresight or extraordinary coincidence. Time will clarify which. The disappearing act behind the Sun. There's a specific term in orbital mechanics that most people never encounter unless they study spaceflight or planetary science. Solar conjunction. It sounds technical, almost bureaucratic, but what it describes is remarkably simple. It's when an object in space passes directly behind the Sun from Earth perspective, becoming completely invisible to our telescopes, because the Sun's overwhelming brightness drowns out everything near it. For 3IATLAS. Solar conjunction happened on October 21st, 2025. The exact same day those trajectory deviations started appearing in independent tracking data. Think about the geometry for a moment. Earth, Sun, 3IATLAS, all lined up in a straight row with the Sun in the middle. From our vantage point, the object vanished into the solar glare, not behind the physical disk of the Sun. That would require precise alignment down to arc seconds, but close enough that the Sun's corona, that super-hot outer atmosphere, our star, extending millions of kilometers into space, creates a blinding background that makes observation impossible. Even our most powerful coronagraphs, instruments specifically designed to block the Sun's disk and study the area around it, struggle to pick out faint comets when they are this close to solar alignment. This alignment doesn't last forever. Objects move, Earth orbits, the geometry shifts. But for 3IATLAS, the timing created something unusual. Solar conjunction on October 21st meant the object entered the zone of unobservability, 8 days before perihelion, 8 days before its closest approach to the Sun on October 29th at 11:36 Universal Time. Those 8 days represent the period when the object would be accelerating to its maximum velocity, experiencing peak solar radiation and, if it were anything other than a natural comet, executing the most critical phase of its mission profile. Let's talk about what happens at perihelion. From an engineering perspective, if you're sending a probe to another star system and you want it to perform maneuvers within that system, you don't do it randomly. You follow the principles of orbital mechanics that have governed spaceflight since we started leaving Earth's atmosphere. The Oberth effect, formulated in the 1920s, tells us that the most efficient time to change a spacecraft's trajectory is when it's moving at its highest velocity. The math is straightforward. Kinetic energy equals 1/2 mass times velocity squared. That squared term matters enormously. If you're moving at 10 kilometers per second and you add 1 kilometer per second of thrust, the energy change is much smaller than if you're moving at 50 kilometers per second and add that same 1 kilometer per second. The faster you're already going, the more energetic punch you get from each unit of thrust. For 3IATLAS, maximum velocity occurs at perihelion. At that point, falling toward the Sun's gravity well, the object will be traveling at approximately 68 kilometers per second relative to the Sun. If you wanted to release probes that could intercept planets in the inner solar system, perihelion is when you do it. A small velocity change at that moment, maybe 10 or 15 kilometers per second in the right direction, could redirect a mini probe toward Earth, Mars, or Venus with relatively modest fuel expenditure. Wait until you're farther out, moving slower, and the same maneuver costs exponentially more energy. This isn't speculation about alien engineering. This is how human spacecraft work. When we send probes to the outer solar system, We use gravity assists to gain speed, and we time our engine burns for moments of peak velocity. The Voyager missions, New Horizons. Every deep space probe follows these principles because physics doesn't care about your intentions. The math works the same, whether you're NASA or something that evolved under a different star. Now overlay that engineering reality onto 3IATLAS's timeline. October 21st. Solar conjunction begins. October 29th. Perihelion passage at 1.356 astronomical units. During those 8 days, Earth-based telescopes see nothing. Mars orbiters might catch glimpses, if they're looking at the right moment. But the Sun's position relative to Mars means even those observations are limited. The European and space agency's JUICE spacecraft, currently between Earth and Jupiter on its way to the outer system, will attempt observations in early November, but during the critical perihelion window. 3IATLAS operates in essentially complete darkness from our perspective. The distance, 1.356 astronomical units, places it about 200 to 3 million kilometers from the Sun. For context, Earth orbits at 1 astronomical unit, Mars at about 1.5. Perihelion for 3. IATLAS puts it closer to the Sun than Mars's orbit, but farther than Earth's. It's a position that offers tremendous solar energy for power generation, if you're a technological system, but not so close that temperatures would vaporize metals or destroy electronics. With proper shielding, a habitat designed to operate in interstellar space, shielded against cosmic radiation and near absolute zero temperatures, would find this distance almost balmy by comparison. The solar radiation flux at that distance would deliver approximately 33 gigawatts of power to the object's surface, assuming Loeb's minimum diameter estimate of 5 kilometers, 33 gigawatts. That's roughly the output of 30 large nuclear power plants. If even a fraction of that could be captured and converted to useful energy, you'd have more than enough to run any conceivable propulsion system, communications array, or manufacturing process. Again, this isn't implying 3IATLAS is technological. It's pointing out that if it were, perihelion would be the ideal moment to do whatever it came here to do, and solar conjunction ensures we won't be watching when it happens. The orbital parameters tell another story that's easy to miss if you're not looking for it. 3. I has an eccentricity of 6.137. Eccentricity is a number that describes how elliptical or hyperbolic an orbit is. A circle has eccentricity 0. Earth's slightly elliptical orbit has eccentricity 0.017. Anything above 1.0 is a hyperbolic trajectory, meaning the object isn't bound to the Sun and will eventually escape. 6.137 is extraordinarily hyperbolic. The trajectory is almost a straight line, barely curved by the Sun's gravity. This object is passing through our solar system at such high speed that even our star's immense gravitational pull only bends its path slightly. That extreme eccentricity means something else too. Time spent in the inner solar system is minimal. 3IATLAS didn't spend months slowly falling toward the Sun like comets from the Oort cloud. It came screaming in from interstellar space at 58 kilometers per second, and will leave at roughly the same speed. The entire passage from discovery in early July to departure from the inner system by late December spans about 6 months. Compare that to long-period comets that can spend years in the inner system, or short-period comets that return every few years or decades. This is a flyby in the truest sense, a brief interaction with the Sun before continuing into the galactic disk. But here's where it gets interesting. The trajectory isn't just hyperbolic, it's aligned. The orbital plane of 3IATLAS matches the ecliptic, the plane defined by Earth's orbit around the Sun, to within 5 degrees. Most objects coming from interstellar space would approach from random angles. The galaxy doesn't care about our ecliptic. Comets from the Oort cloud, gravitationally bound to the Sun, but barely. come from every direction imaginable. That's why we see them scattered across the sky. Retrograde orbits, prograde orbits, high inclinations, low inclinations, there's no preferred direction. 3IATLAS is different. Its inclination of 175 degrees means it's moving retrograde, opposite to the direction planets orbit. But the plane itself is nearly aligned with ours. Loeb calculated the probability of that alignment occurring by chance at roughly 0.2%. That's not impossible, 2 in 1,000, but it's uncommon enough to raise eyebrows. A trajectory aligned with the planetary plane makes interception easier if you're trying to release probes that will encounter multiple planets, starting from a trajectory already in their orbital plane. Saves enormous amounts of fuel compared to making major plane changes, which are among the most expensive maneuvers in orbital mechanics. Add the timing. The arrival time of 3IATLAS brings it within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, and Jupiter on March 16th, 2026. The probability of a random interstellar object happening to pass close to 3 major planets during its flyby is vanishingly small. Loeb and his colleagues calculated it at roughly 0.005%, 5 in 100,000. These aren't impossible odds, but they're starting to accumulate in ways that make pattern recognition circuits in our brains light up. Is it coincidence that perihelion happens during solar conjunction from a physics standpoint? There's no connection. Solar conjunction is about Earth's position relative to the object's trajectory. Perihelion is about the object's closest approach to the Sun. They're independent parameters. The fact that they occur 8 days apart. Creating a window where the object is both at peak velocity and hidden from observation is just how the orbital geometry worked out. But if you were planning an interstellar mission and could choose your approach vector, you'd absolutely design it this way. Hide the most critical phase behind the brightest object in the system. The question becomes testable on November 3rd. When 3IATLAS emerges from behind the Sun, we'll have clear lines of sight again. Multiple observatories will track its position, measure its brightness, and analyze its spectrum. If the trajectory deviations observed in late October were real and sustained, they'll show up in the post-perihelion data. The offset should be larger, the divergence from purely gravitational motion more obvious. If those deviations were measurement errors or temporary outgassing anomalies, the object will return to its predicted path and all the speculation evaporates. But there's a third possibility that keeps astronomers up at night. What if the trajectory matches predictions perfectly after perihelion, but the spectroscopic signature changes? What if the composition looks different? The activity level drops or spikes in unexpected ways. The polarization shifts. Loeb has said publicly that if 3IATLAS survives perihelion intact and continues showing natural comet characteristics, he'll downgrade it to rank 2 on his scale. Still anomalous, still interesting, but probably natural. However, if post-perihelion observations reveal anything unusual, changes that suggest the object is no longer the same system we were tracking before it disappeared, then rank 4 might not be high enough. There's historical precedent for comets behaving strangely at perihelion. They break apart from thermal stress. They flare unexpectedly as fresh ice gets exposed. They fade rapidly if their volatile reservoirs are exhausted. Comet Ison. In 2013, disintegrated completely during its perihelion passage, providing a spectacular example of how violent these environments can be. But Ison was on a much closer trajectory, skimming just over 1 million km above the Sun's surface. 3IATLAS is staying a comfortable 203 million km away, far enough that thermal stresses should be manageable, even for a loosely bound rubble pile. The mass estimates suggest something durable, at least 33 billion tons, based on the lack of non-gravitational acceleration. Despite visible outgassing, that mass combined with a diameter around 5 km implies an object that's either incredibly dense or has significant structural integrity. Most comets are loosely bound ice and rock, porous structures that sublime and shed material easily. If 3IATLAS is that massive and hasn't shown trajectory changes from outgassing, either the outgassing is perfectly symmetric, which seems unlikely given the observed and anti-tail that existed in July and August, or the object's mass is large enough that even vigorous outgassing produces negligible recoil. Either way, it's built to last. Perihelion at 1.356 astronomical units isn't going to destroy it. The question is what it does during those hidden days. Does it break apart naturally, creating fragments that will become visible as they separate over the following weeks? Does it release material intentionally, smaller objects that begin their own trajectories towards specific targets? Or does it simply continue on its hyperbolic path unchanged, except for the expected brightening and possible increase in outgassing from solar heating? We're about to find out. By the time November arrives, 3IATLAS will have completed its close approach, absorbed 33 gigawatts of solar radiation over several days, and, if it's anything other than a comet, executed whatever maneuvers or deployments were planned for this moment. The post-perihelion observations will either confirm it's natural, revealing nothing unusual despite the earlier anomalies, or they'll show something that forces us to take the technological hypothesis seriously. There's no middle ground anymore. The data either supports natural explanations or it doesn't. And somewhere between Earth and that hidden point behind the Sun, during 8 days when no telescope can watch, Atlas does what it came here to do. The brightness paradox. Brightness in astronomy isn't just about how much light reaches your telescope. It's a diagnostic tool, a way of reading what an object is made of, how active it is, how much surface area is exposed to solar radiation. When a comet approaches the Sun, predictable things happen. Ice sublimates, turning directly from solid to gas. That gas drags dust particles off the nucleus, creating the familiar coma and tail. The coma scatters sunlight, making the comet appear brighter. The closer to the Sun, the more heating, the more sublimation, the brighter the display. This relationship is so reliable that astronomers can predict comet brightness months in advance with reasonable accuracy. 3IATLAS broke that pattern. The Jet Propulsion Laboratory's predictions, based on standard models of cometary behavior and the object's known size and trajectory, expected an apparent magnitude near 14.8 in late October. Magnitude is a logarithmic scale where lower numbers mean bright to objects. The difference between magnitudes 14 and 15 might not sound like much, but each full magnitude represents about 2.5 times more or less light. So, magnitude 15.1, what observers actually measured, means the object was roughly 26% dimmer than expected. That might seem like a minor discrepancy. Comets are unpredictable. Their activity waxes and wanes. Rotation can hide or expose active regions. Dust production varies based on composition. All of this creates uncertainty in brightness predictions. But here's what makes this particular dimming so puzzling. The James Webb Space Telescope confirmed active outgassing. Spectroscopic observations showed carbon dioxide, water vapor, carbon monoxide, cyanide, and ionized nickel streaming off the nucleus. The production rates measured by Webb suggested the object was losing approximately 25 kilograms per second during observations in late August. That's not a dormant comet. That's an active system shedding material at rates comparable to many solar system comets. When you have that much outgassing, you create a substantial coma, a cloud of gas and dust surrounding the nucleus. That coma scatters sunlight. The more material in the coma, the more scattering, the brighter the comet appears from Earth. Standard photometric models account for this. You measure the production rate of gas, estimate the dust-to-gas ratio based on spectroscopy, calculate how much sunlight that dust will scatter, and predict the resulting brightness. For 3IATLAS, those calculations suggested magnitude 14.8. Instead, telescopes saw 15.1. The first explanation that comes to mind is composition. Maybe 3IATLAS has an unusually low dust-gas ratio. Pure gas doesn't scatter visible light as efficiently as dust particles. If the object is ejecting mostly volatiles with very little particulate matter, the coma would be less reflective than expected, producing a dimmer appearance despite high activity. That's plausible. Interstellar comets might form under different conditions than solar system comets. Different temperatures, different pressures, different chemical environments could produce objects with unusual ratios of ice to dust. But Webb's spectroscopic analysis showed dust signatures, silicates, organic compounds, the kind of particulate matter that should scatter light effectively. The spectrum wasn't that of a purely gaseous coma. There was solid material present. So the low dust hypothesis doesn't quite work unless the dust grains are much smaller than typical comet dust. Very small particles, smaller than the wavelength of visible light, scatter less efficiently. They could explain reduced brightness despite confirmed dust presence. That's possible, though it requires another unusual characteristic stacked onto an already unusual object. The second explanation involves geometry and viewing angle. Comets aren't spherically symmetric. They have jets, localized regions of activity where sublimation is concentrated. If the main active regions on 3IATLAS are pointed away from Earth, we might be seeing primarily the reflected sunlight from the nucleus itself, rather than the bright, scattered light from the coma's dust. This happens with solar system comets. Occasionally, a comet can be very active, but appear relatively faint from Earth if we're viewing it from an unfavorable angle. Except we have confirmation of a visible coma. Hubble images from July showed a distinct teardrop-shaped cocoon of material trailing the nucleus. The anti-tail observed through August demonstrated asymmetric outgassing strong enough to create a visible structure pointing toward the sun. If jets were active enough to produce those features, they should be bright enough to show up in integrated brightness measurements. The viewing angle explanation only works if the geometry changed dramatically between the Hubble observations in July and the brightness measurements in October, and there's no obvious reason why that would happen. Then there's the possibility of surface changes. Comets can develop insulating crusts, layers of dust and organic material that reduce sublimation rates as the surface heats. Fresh ice sublimates quickly when first exposed to solar radiation. Over time, this volatile ices are lost, leaving behind a lag deposit of less volatile material that acts like a blanket, slowing heat transfer to subsurface ice. This process makes comets fade as they age. An interstellar comet, having spent potentially billions of years in deep space at temperatures barely above absolute zero, might have all its volatile surface ice locked away under such a crust. As it approaches the sun, that crust heats up but doesn't necessarily lead to proportional increases in activity. The object could be outgassing vigorously from localized fractures or weak spots, while most of its surface remains dormant. That scenario fits some of the observations. High activity in specific regions creating the observed mass loss, but overall dim appearance because most of the surface isn't contributing to the coma. It's a reasonable natural explanation, but it creates another question. If the surface is largely inactive, where is all that carbon dioxide coming from? Webb measured substantial carbon dioxide production, much higher than the water production rate. Carbon dioxide sublimation requires specific temperature thresholds. It suggests either exposed carbon dioxide ice or subsurface reservoirs connected to the surface through cracks or vents. Either way, you'd expect to see regional brightening around those active areas, hot spots that would show up in high-resolution imaging. The high-rise observations from Mars Reconnaissance Orbiter could potentially resolve this. With a pixel scale of about 30 kilometers, they should be able to distinguish between a uniformly dim object and one with bright active regions concentrated in specific areas. But those images remain unreleased. Without them, We're left inferring structure from integrated brightness measurements and low-resolution spectroscopy, trying to build a three-dimensional model from two-dimensional shadows. There's another angle to consider here, one that sounds almost conspiratorial, but emerges from the data itself. What if the object is deliberately minimizing its brightness? That sounds absurd for a natural body. Comets don't have intentions. They respond to solar heating according to the laws of thermodynamics. But if 3IATLAS were artificial, a probe or spacecraft rather than a comet, brightness management would be a basic operational parameter. Think about human spacecraft design. We coat surfaces with specific materials to control thermal properties and minimize reflectivity when necessary. Stealth satellites use low albedo coatings to reduce visibility. If you're sending a probe across interstellar space, and you want it to pass through a planetary system unnoticed, or at least unremarkable, you design it to look like natural debris, but looking natural from spectroscopy. Having the right chemical signatures is easier than matching brightness curves perfectly. You can outgas water and carbon dioxide intentionally, mimicking comet activity. Controlling the exact magnitude at which you appear requires either perfect matching of surface properties or deliberate dimming through geometry, orienting reflective surfaces away from observers. I know how this sounds. We're reaching for technological explanations for what could simply be an unusual but natural comet with a typical composition and structure. The brightness paradox alone doesn't prove anything. Comets surprise us regularly. They flare unexpectedly, fade without warning, split into fragments, exhibit jets that defy modeling. 3IATLAS being dimmer than predicted isn't extraordinary by itself, but place it in context. An object that's dimmer than expected despite confirmed high activity. An object showing trajectory deviations from predicted paths. An object with geometric light patterns that might indicate structured plasma fields. An object with composition anomalies like nickel emission without corresponding iron. An object arriving on a trajectory optimally aligned, with the planetary plane and time to pass multiple planets. Each piece individually is explainable, but together they form a pattern that's harder to dismiss. The brightness measurements continue through early November. As 3IATLAS emerges from behind the Sun, observatories worldwide will track its magnitude, looking for the expected post-perihelion brightening. Standard comet models predict significant brightness increases after perihelion as fresh material gets exposed and outgassing intensifies from solar heating. If 3IATLAS follows that pattern, brightening to magnitude 12 or 11, as some predictions suggest. It supports natural explanations. The October dimness was just an artifact of viewing geometry or a temporary reduction in activity. But if the object remains dimmer than predicted, if it continues operating below expected brightness despite proximity to the Sun and confirmed outgassing, then we have a sustained anomaly that demands explanation. Systematic dimming implies something about the object's structure or behavior that current comet models don't capture. Either our understanding of interstellar comet composition is fundamentally wrong, or 3IATLAS is managing its observational signature in ways natural objects don't. The polarization measurements add another layer. In late September, the Very Large Telescope team observed 3IATLAS and found extreme negative polarization values. Polarization describes how light waves are oriented after scattering off particles. Different materials and particle sizes create characteristic polarization signatures. Most comets show positive polarization, meaning the scattered light waves align perpendicular to the scattering plane. 3IATLAS showed strong negative polarization, with waves aligned parallel to the scattering plane. That behavior is almost unprecedented in comets. The VLT team noted the probability of such extreme polarization occurring naturally in a comet is below 1%. Negative polarization can happen with very specific particle size distributions and compositions. Laboratory studies show certain types of dust can be produced under controlled conditions. But finding it in an active comet where particle sizes vary widely and composition is mixed is extraordinarily rare. It suggests either the dust from 3IATLAS is remarkably uniform in size, or its particles are clustered around some optimal diameter for producing negative polarization, or the composition includes materials with unusual optical properties, not commonly found in solar system comets. Or third option, the polarization isn't coming from scattered sunlight at all. It's emission from some other process that happens to produce polarized light. Synchrotron radiation from charged particles spiraling in magnetic fields produces highly polarized emission. So do certain plasma processes, if what we're seeing isn't reflected sunlight, but rather emission from a magnetized plasma surrounding the object. The polarization signature would look very different from typical comet dust scattering. This is speculative, venturing into explanations that require exotic physics or technological processes. But when standard models fail to explain observations, you have to consider alternatives. The brightness paradox isn't going to resolve itself through observation alone. We need close-up imaging, resolved surface features, thermal mapping that shows where heat is being generated and radiated. We need to distinguish between a cold, mostly inactive surface with localized hotspots and a uniformly active surface that's somehow dimmer than expected. The difference matters enormously for determining what 3IATLAS actually is. For now, we watch and wait. November 3rd brings renewed visibility. December 19th brings closest approach to Earth at 1.8 astronomical units, about 269 million kilometers. That's not close enough for amateur telescope observation, but professional facilities will have excellent viewing geometry. The brightness curve through November and December will tell us whether October's dimness was an aberration or a persistent characteristic. If the object brightens as predicted, following standard comet behavior, the anomaly fades into statistical noise. If it stays dim, or worse, gets dimmer while maintaining high outgassing rates, then we have something that defies comfortable explanation. The universe is full of objects we don't fully understand. Interstellar space is vast and ancient, producing conditions we can't easily replicate or study. 3IATLAS being unusual doesn't make it artificial, but unusual, unpredictable ways, following patterns that just happen to align with what you'd design if you wanted to traverse a planetary system efficiently while minimizing detection. That's when unusual starts looking like something else entirely. Geometric plasma structures. Plasma is the fourth state of matter after solid, liquid, and gas. When you heat a gas enough, electrons tear away from atoms, creating a soup of charged particles that behaves very differently from neutral matter. Lightning is plasma. The sun's corona is plasma. The aurora borealis streaming across polar skies is plasma, interacting with Earth's magnetic field. It's everywhere in the universe, making up 99% of visible matter. But it's also notoriously difficult to control. Plasma responds to electromagnetic fields, flows along magnetic field lines, forms structures and instabilities that challenge our best physics models. Natural plasmas in cometary environments are chaotic. Solar wind. Moving, charged particles streaming from the sun at hundreds of kilometers per second. Interacts with the comet's coma. That interaction creates a bow shock, a boundary where solar wind slows and compresses. Behind the shock, you get complex turbulence, eddies, and irregularities. The result is a diffuse, irregular glow. When you image comets in certain wavelengths, you might see asymmetries, brighter regions where outgassing is stronger. But overall, the light distribution is smooth, following the density gradients of gas and dust in the coma. What you don't typically see is geometry-sharp boundaries, color separation into distinct zones, cross patterns, or other regular shapes. The physics doesn't support it. Plasma, without strong external organizing forces, spreads, diffuses, follows pressure gradients and magnetic field lines that themselves, ELVs, are tangled and irregular around comets. Getting structured geometry requires either very specific conditions or active field management. On October 20th, David Sarita reviewed images from NASA's LASCO C3 coronagraph. These instruments photograph the space around the Sun by blocking the solar disk with an occulting disk, revealing the faint corona and any objects passing through the field of view. Comets show up occasionally, usually as fuzzy blobs with tails streaming away from the Sun. Sarita found 3IATLAS in multiple frames. What caught his attention wasn't the object's presence, but its appearance in one image. The light distribution around 3IATLAS formed what he described as a cross pattern. Not a perfect geometric cross like you draw on graph paper, but a distinct fourfold symmetry with brighter regions extending in perpendicular directions. Then, in the next several frames, the object disappeared entirely. LASCO takes images at regular intervals, typically every 12 or 30 minutes, depending on the observation program. Objects in the coronagraph's field of view should appear in consecutive frames. As they move through space, they might change brightness slightly due to viewing geometry or activity variations, but they don't vanish and reappear unless something dramatic happens. 3IATLAS vanished for multiple frames, then reappeared, then vanished again. The pattern repeated several times across the observation sequence. Sarita documented this and shared the findings publicly, arguing that the disappearances and geometric patterns suggested something unusual about the object's behavior or structure. Skeptics immediately offered alternative explanations. LASCO images are challenging to interpret. The instrument wasn't designed for deep space observations. It's optimized for solar corona studies, which means its sensitivity and calibration are tuned for specific brightness ranges and wavelengths. Faint objects near the detection limit can appear and disappear due to image processing artifacts. Cosmic ray hits on the detector, or simple signal-to-noise fluctuations, if 3IATLAS was at the edge of LASCO's detection threshold. Frame-to-frame variations in background noise could make it visible in some images and invisible in others. The cross pattern could be a diffraction artifact. Coronagraphs use complex optical systems with multiple occulting disks and baffles to block sunlight. Bright point sources sometimes create cross-shaped diffraction spikes due to the edges of these optical elements. Stars in LASCO images often show this pattern. If 3IATLAS had a bright central region, a concentrated nucleus, or a particularly reflective spot, it could theoretically produce similar diffraction effects. But the group that documented the trajectory anomalies did independent analysis. They were processing their own observations from ground-based facilities using standard astronomical CCD cameras attached to moderate aperture telescopes. They applied single-image enhancement, adjusting contrast and brightness to bring out faint details. But they didn't stack multiple exposures or use heavy processing that might create artifacts. Their images showed color separation in the coma, green outer regions, blue central areas, pink zones distributed around the nucleus. To verify this wasn't an artifact, they imaged reference stars in the same field of view. Spica, one of the brightest stars visible from Earth, appeared as a tight circle, a killer point spread function with normal color balance. Comet C, 2025 R2 Swan, another active comet visible in the same region of sky, showed a typical cometary appearance with a diffuse circular coma and faint tail. No geometric patterns. No unusual color separation beyond the slight green tint common in cometary coma from diatomic carbon emission. 3IATLAS looked different. The color zones they measured correspond to known emission lines. Green from ionized cyanogen, blue from hydrogen plasma, I think likely from a mix of ionized carbon and other species. These aren't unexpected chemicals. The Keck Observatory confirmed cyanogen presence back in August. Hydrogen emission is standard for comets. What's unusual is the spatial distribution. Normally, these emission regions overlap. You don't get clean separation because the gases mix as they expand from the nucleus. Turbulence, solar-wind interaction, and thermal diffusion blur any initial structure within seconds to minutes after material leaves the surface. Maintaining distinct color zones requires something preventing mixing. In laboratory plasmas, that something is usually a magnetic field. Charged particles spiral along magnetic field lines, confined to specific regions depending on the field geometry. If you arrange magnetic fields carefully, you can create structured plasmas with well-defined boundaries between regions of different temperature composition. We do this in fusion reactors. We do it in plasma thrusters for spacecraft. It requires active field coils or permanent magnets with specific configurations. Natural magnetic fields around comets are weak and irregular. Comets don't have internal dynamos like planets. They're not massive enough or electrically conductive enough to generate strong, self-sustained magnetic fields. They do carry embedded magnetic fields, frozen into the material from their formation environment. But these fields are typically chaotic, with no large-scale organization. The solar wind brings its own magnetic field, but that's equally disorganized at the small scales relevant to comet comas. Could 3IATLAS have an unusually strong or well-organized internal magnetic field? It's not impossible if the object formed in a region with strong ambient fields, perhaps near a massive star or in a molecular cloud with aligned magnetic fields. It might have retained some of that structure. Certain minerals, like magnetite, can preserve magnetic fields over geological timescales. If 3IATLAS has a high concentration of magnetic minerals and they're aligned, you could theoretically get a weak but organized field. But here's the problem with that explanation. The field would need to be strong enough to organize plasma over distances of hundreds to thousands of kilometers. The scales involved are the nucleus itself, which might be 5 to 10 kilometers across. There, the coma, the extended cloud of gas that can reach tens of thousands of kilometers in size. For active comets, creating structured plasma at those scales requires field strengths that far exceed what remnant magnetization in rocks can provide. You'd need active generation, current loops, moving charged particles, creating magnetic fields through electromagnetic induction. The alternative is that what we're seeing isn't plasma structure at all. It's an optical effect, selective scattering of sunlight by particles with specific properties distributed in patterns around the object. Certain dust grain compositions preferentially scatter light at particular wavelengths. If 3IATLAS is ejecting different types of dust from different regions of its surface, and those dust types separate spatially as they move away from the nucleus based on size and composition, you could create zones of different color. This happens to some degree in all comets. Heavier particles follow slightly different trajectories than lighter particles, but getting the clean separation observed by Earth exists, would require the ejection processes to be extremely organized. Each type of material would need to come from distinct surface regions and maintain that separation as the coma expands. It's difficult but not physically impossible. Some comets show jets with distinct colors when imaged in narrow band filters that isolate specific emission lines. What bothers careful observers is the combination, color separation, plus geometric patterns, plus the disappearing act in LASCO images, plus the trajectory anomalies, plus the brightness paradox. Each piece has potential natural explanations that stretch but don't break physics. All of them together start to feel less like a coincidence, and more like a system with behaviors we're not equipped to interpret. There's a concept in SAT research called the Drake equation, but there's another less famous framework called the Rio scale. It's designed to quantify the significance of SETI detections, ranking signals from 0, meaning obviously natural or human-made interference, to 10, meaning unambiguous evidence of extraterrestrial technology. The scale considers factors like distance from Earth, information content of the signal, whether it can be independently verified, and how well it fits natural explanations versus artificial ones. 3IATLAS doesn't fall neatly onto the Rio scale because it's not a signal. It's a physical object. But if you tried to apply similar logic, the geometric plasma structures would score somewhere in the middle range. Are not definitive, not easily explained by standard models, requiring multiple observations from independent sources to verify, potentially natural if you allow for unusual but physically permissible conditions, but accumulating enough auditors that ignoring them becomes harder to justify than investigating them seriously. The plasma patterns also raise practical questions about observation priorities. If what we're seeing is real structure in the coma, not artifacts or illusions, then we need high-resolution spectroscopic imaging. Not just single wavelength photos, but hyperspectral data cubes that show how each emission line is distributed spatially. That kind of data would immediately distinguish between organized plasma with sharp boundaries and complex optical effects from dust scattering. It would tell us if magnetic fields are involved, if electric currents are flowing through the coma, if something about this object creates electromagnetic environments unlike any comet we've studied. JUICE spacecraft observations in early November might provide some of that data. The spacecraft has spectrometers and particle detectors that could characterize the plasma environment if it gets close enough and points its instruments correctly. But JUICE is optimized for studying Jupiter's moons, not interstellar comets. The observation window will be limited, and the geometry might not be ideal for resolving. Fine spatial structure ground-based observations will continue after 3IATLAS emerges from solar conjunction. Amateur astronomers with good equipment can capture your images showing the overall coma morphology. Professional facilities with adaptive optics and integral field spectrographs can do detailed analysis. The question is whether the patterns persist or are transient features specific to the object's state in October. If the geometry disappears, we can argue it was always artifacts or temporary phenomena related to the perihelion passage. If the patterns remain, if subsequent observations by multiple independent groups all confirm structured light distribution with color separation and geometric regularity, then we have a genuine mystery that demands explanation beyond hand-waving about unusual conditions. Plasma physics offers tools for diagnosing these situations. You can model expected plasma behavior around a comet, incorporate solar wind parameters, estimate magnetic field strengths needed to produce observed structures, and compare those requirements to known natural sources. If the analysis shows that maintaining the observed geometry requires conditions that can't plausibly exist in a natural comet environment, you're left with two options. Either our models of plasma physics are incomplete, or 3IATLAS isn't relying solely on natural processes. The cross pattern in particular bothers physicists familiar with plasma confinement. Fourfold symmetry is common in engineered magnetic traps, where coils are arranged in quadrupole configurations. Nature rarely produces such clean symmetry without very specific forcing. You see it in crystals, where atomic lattices dictate structure. You see it in some planetary magnetospheres, where geometric effects from rotation and solar wind interaction create organized patterns. But in a cometary coma, far from any rotating body with weak or non-existent internal magnetic fields, getting a cross pattern is hard to justify with standard physics. We'll know more by December. By then, the object will be far enough from the sun that imaging won't be fighting solar glare. The geometry will be favorable for Northern Hemisphere observatories. High-resolution photometry and spectroscopy will either confirm the plasma structures are real and persistent, or show they were observational artifacts specific to difficult viewing conditions in October. Either answer is important. If they're artifacts, we learn about the limitations of our detection methods and the care needed when interpreting faint object images. If they're real, we face something that challenges our understanding of how comets work or forces us to seriously consider that 3IATLAS might not be a comet at all. The jet flip anti-tail becomes tail. Comet tails are one of the most recognizable features in astronomy. They point away from the sun, always stretched by solar wind and radiation pressure, into long streamers that can extend millions of kilometers into space. The physics is straightforward. Sunlight carries momentum when photons hit dust particles ejected from a comet. They transfer that momentum, pushing the particles away from the sun, the solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Does the same thing to ionized gas. Both effects work in the same direction, away from the source of radiation and wind, creating the classic comet tail. Sometimes you see two tails. A dust tail curved slightly because dust particles are massive enough that their orbital motion matters, and an ion tail, straight and often bluish, made of ionized gas that responds primarily to the solar wind's magnetic field. Both point away from the sun. This is so fundamental to cometary behavior that it's one of the first things you learn in introductory astronomy. Tails point away, always, except when they don't. Anti-tails, properly called enthelion tails or sunward spikes, are rare but documented features where material appears to stream toward the sun rather than away from it. The name is slightly misleading because it's usually an optical illusion. Perspective effects when viewing the comet from certain angles can make part of the tail appear to project forward. Imagine looking at a curved structure nearly edge-on. The parts of the curve that extend toward you look like they're pointing in the opposite direction from the parts extending away. Enthelion tails result from viewing geometry, not actual sunward motion of material. 3IATLAS showed something different. The Hubble Space Telescope imaged it on July 21st, capturing a high-resolution view of the coma and surrounding material. The image revealed a pronounced sunward spike, material extending from the nucleus in the direction of the sun. Not a subtle perspective effect. A clear, distinct structure with about 2-to-1 elongation in the projected view. But when Avi Loeb and Eric Quito corrected for viewing angle, they calculated the three-dimensional elongation was approximately 10-to-1. That's a jet, not an optical illusion. The physics of creating a sunward jet is counterintuitive. You're fighting radiation pressure and solar wind. Both want to push material away from the sun. To create a jet aimed sunward, you need a mechanism that overcomes those forces. The explanation Loeb and Quito proposed in their September paper involves the specifics of how ice sublimation works. When carbon dioxide ice on the comet's surface absorbs solar radiation, it sublimates, turning directly from solid to gas. That gas expands rapidly, carrying with it water ice fragments that were embedded in or resting on the carbon dioxide ice. Those ice particles, now separated from the surface, scatter sunlight efficiently, creating the visible glow we see as a coma, but they also sublime. Water ice at the temperatures relevant here, a few hundred Kelvin, doesn't last long. The ice particles themselves turn to gas. Over time, scales of minutes to hours depending on their size. If the sublimation process ejects ice particles with significant velocity, those particles start sublimating immediately and create a stream of material that moves away from the nucleus but continually loses mass. The trick is timing. At distances of 3 to 4 astronomical units from the sun, water ice sublimation produces a peak in the scattering cross-section. There's enough solar heating to sublime the particles quickly, but not so much that they vanish instantly. The balance creates a region where the density of light scattering ice particles is maximum. If that maximum density region happens to be offset toward the sun from the nucleus, you get an anti-tail. The particles are moving outward in all directions from the comet, but the ones moving sunward last longer before fully sublimating. Compared to the ones moving away from the sun, that asymmetry in particle lifetime creates an apparent asymmetry in the brightness distribution. It's still an optical effect in some sense, not truly sunward motion. But it's based on real physics of how sublimation rates vary with heliocentric distance. That's the natural explanation for what Hubble saw in July. It works mathematically. The model Loeb and Quito published fits the observed elongation ratios and brightness distributions, but it also predicts something specific. As 3IATLAS continues approaching the Sun, moving from 4 astronomical units inward to 2, then to perihelion at 1.356, the sublimation rates should change. Water ice particles ejected at closer distances sublimate faster. The peak scattering region shifts. Eventually, the anti-tail structure should disappear, replaced by more symmetric outgassing and then potentially by a traditional tail as refractory dust that doesn't sublime quickly begins to dominate the coma. In September, new images from the Nordic Optical Telescope in the Canary Islands confirmed the prediction. The anti-tail had diminished. In its place, a faint tail extended away from the Sun, the normal configuration you'd expect from a comet. David Jewett and Jane Liu published the analysis in mid-October, documenting the transition with photometric measurements showing the change in mass flow geometry. This should be satisfying. A prediction made, tested, confirmed, natural comet behavior explained by well-understood physics. The anti-tail wasn't evidence of propulsion or technological control, just sublimation physics playing out exactly as theory suggested. Case closed. But here's where Adam Hibbard, one of Loeb's colleagues at Harvard, raised an uncomfortable question. If you were operating a spacecraft and wanted to slow down as you approached a star system, you'd fire your engines in the direction of travel, creating thrust that opposes your velocity. That's called a retrograde burn in spaceflight terminology. The exhaust would stream ahead of the spacecraft, creating a visible plume pointing toward your destination. From an external observer's perspective, it would look exactly like an anti-tail material extending toward the Sun, opposite the expected direction. Then, as you complete your braking maneuver and need to adjust your trajectory for planetary encounters, you might reverse thrust orientation, fire the engines in the opposite direction to provide acceleration or make course corrections. That exhaust would stream behind the spacecraft, creating a traditional tail-like structure. Again, from an observer's perspective, it would appear identical to what 3IATLAS just did anti-tail in July and August, a transition period in September. Normal tail by October. The timing fits disturbingly well if 3IATLAS were a spacecraft executing a deceleration burn followed by perihelion maneuvering. The sequence of anti-tail to tail transition would occur over exactly the timescale observed. The total mass ejected, about 2 million tons, according to integrated production rate measurements, represents roughly 0.0005 of the object's total mass. That's a surface layer about 4 centimeters thick. If spread evenly across a 5-kilometer diameter sphere, for a natural comet, 4 centimeters of ablation is trivial. Comets regularly lose meters of surface material during perihelion passages. The amount lost tells us almost nothing about what's underneath. For a spacecraft with a protective coating designed to mimic comet activity while shielding internal systems from solar radiation, 4 centimeters is exactly what you'd expect enough material to create convincing spectroscopic signatures and visible activity, but not so much that you risk exposing underlying structure. Loeb has been careful to acknowledge that the natural explanation for the jet flip is perfectly adequate. The Quito-Loeb model doesn't require anything exotic. It's standard thermodynamics and radiative transfer. The sublimation rates, particle sizes, and scattering properties all fit within normal ranges for cometary materials. If you showed these observations to most planetary scientists without mentioning 3IATLAS's other anomalies, they agree it's consistent with a comet transitioning from distant, cold activity dominated by carbon dioxide to closer, warmer activity where refractory dust becomes important. The problem is those other anomalies don't go away. The trajectory deviations, the brightness paradox, the geometric plasma patterns, the composition oddities like nickel without iron, extreme negative polarization, the orbital alignment with the ecliptic, and the timing that brings it close to multiple planets. Each piece has natural explanations, but each natural explanation requires different special conditions: unusual composition to explain the nickel, unusual dust properties to explain the polar, unusual magnetic fields to explain the plasma geometry, unusual viewing geometry to explain the brightness at some point. Invoking multiple independent unusual conditions becomes less parsimonious than considering a single explanation that accounts for everything if 3IATLAS is technological, a probe or spacecraft rather than a natural comet. Then all the anomalies resolve into expected behavior for an engineered system operating in an environment it wasn't originally designed for. The composition reflects manufacturing processes rather than natural formation. The trajectory reflects deliberate navigation rather than gravitational freefall. The brightness management reflects operational priorities, like power generation or thermal control, rather than simple thermodynamic response to solar heating. The jet orientations reflect propulsion system operation rather than an asymmetric sublimation. Trajectory remain purely gravitational or show continued deviations. Do we see any evidence of fragments or secondary objects separating from the main body? Avi Loeb has stated publicly that if 3IATLAS behaves naturally through the perihelion passage and subsequent observations, he'll downgrade its ranking on his scale to 2, meaning unusual but probably natural. The anomalies would remain interesting, worthy of study, but not indicative of technology. However, if the post-perihelion data shows anything inconsistent with natural evolution, if the object continues to defy standard comet models in systematic ways, then the technological hypothesis becomes harder to dismiss. We're watching a test unfold in real time. Nature has given us an interstellar visitor with enough oddities to raise questions, but not enough clear evidence to force conclusions. The jet flip, the transition from anti-tail to tail, is one piece of that puzzle. Understood in isolation, it's unremarkable. Understood in context with everything else 3IATLAS has shown us, it becomes one more data point in a pattern that refuses to resolve into comfortable familiarity. By mid-December, when the object reaches its closest approach to Earth, we'll have months of post-perihelion observations. The tail behavior will be well documented, the trajectory thoroughly measured, the spectroscopic evolution carefully tracked. Either all of that data will converge on natural comet explanations, or it won't. If it doesn't, if 3IATLAS continues being systematically unusual in ways that align with engineered behavior, then the conversation changes from whether we should consider the technological hypothesis to what we do about it. IAWN Planetary Defense Activation. The International Asteroid Warning Network doesn't make announcements lightly. Established under United Nations coordination in 2013, IAWN exists for one purpose: to detect, track, and characterize objects that might pose collision threats to Earth, near-Earth asteroids, comets on intersecting orbits. Anything with even a remote chance of impact gets flagged, analyzed, and monitored until its trajectory is fully understood. It's a global collaboration involving space agencies, observatories, and research institutions across dozens of countries. When IAWN issues a campaign notice, it means something has triggered their threat assessment protocols. On October 21, 2025, the same day 3IATLAS entered solar conjunction, IAWN released an editorial notice through the Minor Planet Center. The announcement declared a coordinated observation campaign targeting 3IATLAS running from November 27th through January 27th, 2026. This marks the first time in IAWN's history that an interstellar object has been designated for planetary defense. Campaign, read that again, and carefully. Planetary defense, not scientific curiosity, not routine monitoring of an interesting visitor. Defense. The language in the announcement attempts diplomatic phrasing, describing the campaign as an exercise to improve astrometric techniques for challenging targets like comets with extended coma and complex morphology. They frame it as a training opportunity, a chance for the global observing community to practice extracting accurate positional measurements from difficult objects. But the subtext is impossible to miss. IAWN doesn't organize 2-month campaigns for objects that pose zero threat. 3IATLAS will pass Earth at 1.8 astronomical units, about 269 million kilometers. That's roughly 700 times farther than the Moon. There is no collision risk. None. The object's trajectory is hyperbolic, meaning it's not even gravitationally bound to the Sun. It's passing through and leaving. So, why is the Planetary Defense Network mobilizing resources typically reserved for potentially hazardous asteroids? The announcement mentioned specific technical challenges. Comets present unique difficulties for astrometry because their Comean tails can pull centroid measurements off the nucleus position. When you measure where a comet is, you're actually measuring the center of light, which might be offset from the physical nucleus by thousands of kilometers if outgassing is asymmetric. This creates errors in trajectory predictions. Fair enough. That's a real problem for comet tracking. But IAWN has never before organized a campaign to address this issue. They've tracked hundreds of comets over the years without needing coordinated international efforts to improve measurement techniques. The timing is also revealing. The campaign begins November 27th, exactly 1 month after perihelion. That's when 3IATLAS will be far enough from the Sun for optimal observation, but still close enough to Earth that parallax measurements from different locations provide a good baseline for distance determination. The campaign ends January 27th, giving a full 2 months of intensive tracking as the object moves away from the inner solar system. 2 months of coordinated observation involving dozens of facilities worldwide, all focused on an object that poses no collision threat. IAWN's announcement includes another unusual element: they're requiring registration and workshop attendance for participation. If you want to join the campaign, you must register by November 7th and attend a technical workshop on comet astrometry techniques. Only participants who complete the workshop can contribute observations to the official dataset. This level of vetting is unprecedented for IAWN campaigns. Typically, they welcome data from any qualified observer. The more telescopes watching, the better the trajectory solution. Restricting participation suggests they want tight control over who contributes data and how that data is analyzed. 3 days before IAWN's announcement on September 30th, Loeb submitted a white paper to the United Nations. In collaboration with colleagues Omar El-Dadi and Gershon Tenenbaum, the paper, titled Advancing Interstellar Science, advocated for exactly what IAWN is now doing: coordinated global observation of interstellar objects to maximize coverage and ensure optimal scientific monitoring. Loeb's argument in the white paper is direct. If interstellar visitors could potentially carry alien technology, even with low probability, the implications for humanity are significant enough that we should treat such objects with the same seriousness as potential impact threats. The white paper uses the term black swan events, situations with small probability but enormous consequences. Standard risk assessment might dismiss low probability scenarios, but when the potential outcome includes first contact with extraterrestrial intelligence, or worse, hostile technology entering our planetary system, probability calculations change. You don't wait for certainty, you act on precaution. IAWN's campaign, launched less than a month after that white paper reached UN committees, suggests someone took the argument seriously. This creates an interesting dynamic. Publicly, space agencies maintain that 3IATLAS is a natural comet, showing unusual but explainable characteristics. NASA's official statements emphasize there's no threat to Earth, and the object will pass safely through the solar system. Tom Statler, NASA's lead scientist for small bodies, has stated on record that all data point to comet classification. The European Space Agency echoes this position. Everything is routine. Nothing to worry about. But behind that public messaging, ABUN, a UN-backed organization specifically tasked with planetary defense, is organizing the most comprehensive observation campaign ever directed at an interstellar object. They're doing it during the exact time window when, if the object were going to do something unexpected, it would become evident. They're restricting participation to vetted observers who've completed specialized training, and they're coordinating with international space agencies to ensure global coverage, meaning no matter where 3IATLAS appears in the sky, multiple facilities will be tracking it simultaneously. The disconnect between public messaging and institutional behavior is stark. If 3IATLAS is just an interesting but harmless comet, why mobilize planetary defense resources? If there's even a small concern that it might be something else, why downplay that possibility publicly while ramping up monitoring privately? One explanation is institutional caution without alarm. Space agencies learned from past communication failures that premature announcements create public panic disproportionate to actual risk. Remember the asteroid Apophis, discovered in 2004, with initial impact probability calculations showing a small but non-zero chance of Earth collision in 2029. Media coverage created widespread concern, before refined observations showed the impact risk was essentially zero. Agencies don't want to repeat that pattern. Better to monitor intensively, gather definitive data, and only make public statements when conclusions are certain. But that explanation assumes the risk is impact-related. 3IATLAS won't hit Earth. The trajectory is unambiguous on that point. So what risk is IAWN concerned about? The campaign announcement doesn't say. It talks about improving astrometry techniques. It mentions the scientific value of studying rare interstellar visitors. It frames everything as opportunity rather than threat. Yet the structure of the campaign, the resources being deployed, the coordination level, all suggest this is being treated as more than scientific curiosity. Loeb's white paper offers a possibility that official channels won't articulate. If 3IATLAS releases secondary objects at perihelion, mini probes or fragments that separate from the main body. Those secondaries could be on trajectories that bring them closer to Earth than the primary object. Detecting and tracking such secondaries requires coordinated observation with high-cadence monitoring. You need multiple facilities watching so that if something separates, it's documented immediately and tracked continuously until its trajectory is fully characterized. The IAWM campaign is designed exactly for that scenario. 2 months of intensive monitoring, multiple observation sites providing redundant coverage, standardized measurement techniques ensuring all positional data is comparable, and workshop training to make sure everyone knows how to distinguish real objects from artifacts or noise. It's a deployment protocol for detecting and tracking unexpected secondaries. Another aspect, rarely discussed publicly, is the possibility of trajectory changes post-perihelion if 3IATLAS executes maneuvers during the hidden period behind the Sun. Those maneuvers might redirect it toward a closer Earth approach than currently predicted. The probability is low, but if you're doing threat assessment, you don't ignore low probability scenarios with high consequence outcomes. Tracking the object intensively immediately after perihelion lets you detect trajectory changes within days rather than weeks, providing maximum warning time. If the approach distance starts decreasing, IAWN's involvement also signals something about internal discussions at government levels. The organization reports to the UN Committee on the Peaceful Uses of Outer Space. For them to approve and resource this campaign required briefings, presentations, and consensus among member states that the monitoring is justified. Whatever data or analysis convince those committees isn't public. We see the output, the campaign itself, but not the input, the evidence or arguments that motivated the decision. There's precedent for this kind of monitoring. When asteroid 2012 TC4 made a close approach to Earth in October 2017, passing within 44,000 kilometers. IAWN coordinated an observation campaign. That campaign had a clear purpose. The asteroid was newly discovered with an uncertain trajectory. Close approaches provide excellent opportunities to refine orbital parameters and assess future collision risk. 2012 TC4 might return someday on a more threatening path. So, gathering data during the 2017 pass was operationally valuable. 3IATLAS is different. It's not coming back. The hyperbolic trajectory means this is a one-time visit. After it leaves the inner solar system in early 2026, it will never return. 50,000 years from now, it will be light years away, traveling through interstellar space towards some unknown destination. So the IAWN campaign isn't about future threat assessment. It's about understanding what's happening now, during this single passage through our neighborhood. The workshop requirement adds another layer. What techniques are they teaching? Standard astrometry is well established. Measuring comet positions isn't fundamentally different from measuring asteroid positions. You account for the extended coma by fitting models to the brightness distribution and extracting the nucleus position. That's routine work. What specific training do observers need that isn't already standard practice? One possibility is detecting faint companions. If secondaries separate from 3IATLAS, they'll be much dimmer than the main object. Standard comet observation techniques optimize for the bright central region. Detecting faint nearby objects requires different processing, different exposure times, and different analysis methods. The workshop might be training observers in those techniques, preparing them to look for things that wouldn't normally be visible in typical comet images. Another possibility is rapid response protocols. If something unexpected appears, IAWN wants immediate notification, not delayed reporting through normal scientific channels. The workshop could establish communication procedures: who to contact, what information to include, how to format the data. Building that network before the campaign starts ensures that if something noteworthy happens, the response is coordinated rather than chaotic. The campaign also serves a diplomatic function by involving observatories from many countries. IAWN ensures that data isn't controlled by a single nation or agency. If discoveries occur, they're immediately internationally shared among all participants. This prevents scenarios where one country monopolizes information about something potentially significant. It's transparency through collaboration, making sure no one can claim secret knowledge or hide important findings. For the public, the IAWN campaign sends a mixed message. On one hand, it's reassuring that serious institutions are monitoring 3IATLAS carefully. If there were genuine concern about threat, we want planetary defense systems engaged and watching. On the other hand, the very fact that they're engaged raises questions about why. What do they know or suspect that justifies this level of attention? The answer is probably more mundane than conspiracy theories suggest. 3IATLAS is genuinely unusual. The combination of anomalies, whatever their ultimate explanation, merits close observation. IAWN seizing the opportunity. Unity to practice coordinated monitoring makes operational sense when a real threat emerges. Someday, having trained international teams experienced in rapid campaign deployment will be valuable. 3IATLAS, threatening or not, provides that training opportunity. But training exercises usually get announced as training exercises, and the language IAWN uses, the structure of the campaign, the restriction on participation, all suggest this is more than practice. It's operational. They're treating 3IATLAS as something that requires active monitoring under protocols normally reserved for objects we're worried about. November 27th is when the campaign officially begins. Between now and then, 3IATLAS completes its perihelion passage, emerges from solar conjunction, and becomes observable again. The first campaign observations will document whatever state the object is in post-perihelion. That initial dataset becomes the baseline for everything that follows. If the object shows changes from pre-perihelion observations, differences in brightness, spectrum, morphology, trajectory, those changes appear immediately on the campaign data. IAWN is positioning dozens of telescopes to watch the reveal. They're coordinating schedules to ensure continuous coverage. They're training observers to look for specific signatures that might indicate something beyond normal cometary evolution. And they're doing all of this under the framework of planetary defense language. That implies they consider 3IATLAS relevant to Earth safety, even though its trajectory poses no impact risk. What they know that we don't remains unclear. What they suspect but won't say publicly is easier to infer, and what they'll find when intensive monitoring begins in late November might finally answer the question that's been growing louder since July. Are we watching the most unusual comet in history, or are we watching something else entirely? The WOW signal connection. August 15th, 1977. The Big Ear radio telescope at Ohio State University was running its routine scan of the sky, searching for patterns in radio emissions that might indicate something other than natural cosmic noise. The telescope wasn't looking for anything specific. It was part of the broader search for extraterrestrial intelligence effort, systematically monitoring radio frequencies in the hope that somewhere, something might be transmitting at 10:16 post-meridian Eastern Time. The telescope detected a signal at 1420 megahertz. That frequency sits right in the middle of the hydrogen line, the radio emission from neutral hydrogen atoms that pervades the galaxy. It's a natural choice for interstellar communication, because hydrogen is the most abundant element in the universe, and any technological civilization would know that frequency well. The signal lasted 72 seconds, exactly the time it takes for Big Ear's beam to sweep past a fixed point in the sky as Earth rotates. Jerry Amen, reviewing the computer printout several days later, saw the intensity spike. The signal was so much stronger than background noise that it stood out immediately. He circled the alphanumeric sequence 6EQUJ5 and wrote in the margin, "WOW." That annotation gave the signal its name, the WOW signal. Nearly 50 years later, it remains one of the most intriguing detections in SETI history. No explanation fully accounts for it. No subsequent observation has ever detected it again, despite decades of follow-up surveys. The signal's origin was traced to a region in the constellation Sagittarius. Right ascension, 19 hours, 25 minutes. Declination, -27 degrees. That's not a point in space. It's a direction. Looking at those coordinates, you're staring toward the center of the Milky Way galaxy through dense star fields and molecular clouds that obscure direct view of the galactic core. Tens of thousands of stars lie within the beam width of Big Ears. Antenna pointed at that location, pinpointing which star, if any, emitted the signals. Impossible without more detections. Fast forward to 2025, 3IATLAS appears in our solar system, the third confirmed interstellar visitor we've ever detected. Its trajectory traced backward through space points to an origin in Sagittarius. Not exactly the same coordinates as the WOW signal. That would be too perfect. But within 9 degrees, 9 degrees on the celestial sphere represents a huge area when you're talking about interstellar distances. But directionally, it's close enough. The Loeb calculated the probability of random alignment at about 0.6%. That number matters. 0.6% isn't impossibly rare. It's not lottery-winning odds, but it's uncommon enough that when you combine it with 3IATLAS's other statistical anomalies, the cumulative probability drops into ranges that make randomness uncomfortable to defend. Multiply 0.6% by the 0.2% chance of ecliptic alignment, by the 0.005% chance of the planetary encounter timing, by the various composition and behavior anomalies, and you quickly reach probabilities measured in parts per quadrillion. Loeb's analysis goes further if the WOW signal originated from 3IATLAS back in 1977. What would that require? First, distance. Where was the object in 1977? Tracing its trajectory backward at 58 kilometers per second. Accounting for gravitational influences from the Sun and planets places it roughly 600 astronomical units from Earth in August 1977. That's about 90 billion kilometers, deep in the outer solar system, beyond the Kuiper belt, but still technically within the Sun's gravitational influence. At that distance, transmitting a signal detectable by Big Ear would require between half a gigawatt and 2 gigawatts of power, depending on the antenna gain and beam focus. That's comparable to a large nuclear power plant on Earth. Not impossible for an advanced civilization, but not trivial either. You don't casually broadcast at those power levels unless you have good reason. The signal was also blue shifted by approximately 10 kilometers per second, meaning the source was moving toward Earth. 3IATLAS is currently moving toward the Sun and, by extension, was moving toward Earth's general direction back in 1977. The Doppler shift matches, not perfect, because measuring precise velocities from a single 72-second signal is difficult, but within the uncertainty ranges, it's consistent. Here's where the speculation becomes both fascinating and frustrating if 3IATLAS transmitted the WOW signal. Why? Loeb suggests it might have been a radar pulse, not a communication attempt. An active sensor sweep, scanning for planetary bodies in the inner solar system. When you're approaching a star system from interstellar space, knowing where the planets are is operationally valuable. You can't see them optically from hundreds of astronomical units away. They're too faint, lost in the star's glare. But if you transmit a powerful radar pulse and listen for reflections, you can detect large bodies and characterize their orbits. Earth would have reflected a tiny fraction of that pulse. Venus would have reflected some. Jupiter, despite being farther from the transmission point in 1977, would have reflected more because of its enormous size. By analyzing the timing and strength of those reflections, if you're patient enough to wait for the round-trip travel time, you could map the inner solar system's architecture. You'd know where to aim your trajectory for optimal planetary encounters decades later, when you finally arrive. The problem with this hypothesis is verification. We have one detection, one 72-second signal that's never repeated. Radio SETI has pointed telescopes back at that region of Sagittarius hundreds of times over the decades. Modern instruments, far more sensitive than Big Ear, have listened across wider frequency ranges and longer integration times. Nothing. The WOW signal remains unique. A singular event with no follow-up, no confirmation, no additional data. That uniqueness is either evidence against the signal being real extraterrestrial communication, or evidence that it was a targeted transmission not meant to repeat. If you're sending a radar pulse to map a solar system, you do it once and move on. Continuous transmission wastes power. The argument cuts both ways. Skeptics say the lack of repetition suggests the PNAUM signal was instrumental error, terrestrial interference, or some transient natural phenomenon. Proponents say directed transmissions wouldn't necessarily repeat, and expecting them to is anthropocentric thinking. Based on how we do radio astronomy, 3IATLAS arriving from roughly the same direction 48 years later adds weight to the radar hypothesis without proving it. Coincidences happen. Sagittarius is a rich region of sky. It's where the galactic center lies, where star density is highest from our perspective, where molecular clouds and stellar nurseries create complex radio backgrounds. An interstellar object coming from that direction and a mysterious radio signal originating from that direction could be completely unrelated. But the timing is uncomfortable. If 3IATLAS left its origin system several million years ago, as seems likely given the distances and velocities involved, it would have been approaching our solar system throughout modern human history, the point when it was 600 astronomical units away, the 1970s, coincides with humanity's first serious attempts at radio SETI. We started listening just as a hypothetical probe would be close enough. That radar scanning of the inner system becomes useful. That synchronicity bothers people. Either it's the most remarkable coincidence in the history of SETI, or it's not a coincidence. If it's not a coincidence, the implication is that something was approaching our solar system for millions of years, and right around the time it got close enough to start active sensing, we happened to develop the technology to detect those transmissions. The odds of that seem impossibly low, unless there's some causal connection we're missing. One possibility is the timing isn't actually remarkable. Human radio technology has only existed for about a century. Radio SETI specifically has operated for maybe 60 years. If interstellar probes are common and they approach solar systems regularly throughout the galaxy, then the probability that one arrives during humanity's brief radio-capable window isn't astronomically small. It's just rare on human timescales. We notice it because we're the ones experiencing it. But cosmically, it's unremarkable. Another possibility involves observer selection effects. We can only detect signals during the time we're listening if probes approach solar systems constantly, but only transmit when they're within certain distance thresholds. We'd only ever detect them if we happen to be listening during that approach window. The vast majority of probes would go undetected, because they arrived before we developed radio astronomy or will arrive after our civilization ends. The ones we detect necessarily correlate with our technological capability. Period. These anthropic arguments dissolve the coincidence without requiring conspiracy or intentionality. They're satisfying in a philosophical sense, but don't really advance our understanding of what 3IATLAS is, or whether the WOW signal connection is meaningful. What would make the connection meaningful is detection of new transmissions. If 3IATLAS emits radio signals as it passes through the inner solar system, signals we can detect and analyze that would transform the hypothesis from speculation into testable science. So far, no radio telescope has reported detecting transmissions from 3IATLAS. That's not surprising if it's a comet. Comets are radio quiet, except for very weak emissions from their comet that require sensitive instruments to detect. But here's the gap. Major radio observatories haven't been systematically monitoring 3IATLAS. SETI programs don't typically point their dishes at comets. Why would they? Comets are natural objects. You aim SETI telescopes at stars, planetary systems, regions of space where you might plausibly find technological civilizations, not at chunks of ice passing through your own solar system. Loeb has called for directed radio observation of 3IATLAS, arguing that the accumulated anomalies justify treating it as a SETI target, regardless of how unlikely the technological hypothesis seems. Point a dish. Listen across the hydrogen line frequency and adjacent bands. See if anything comes up beyond background noise. The cost is minimal, a few hours of telescope time. The potential payoff if something is detected is enormous. Yet, as of late October, no major facility has announced plans to conduct such observations. Part of the resistance comes from institutional conservatism. SETI operates on limited budgets with competitive proposals for telescope time. Pointing at 3IATLAS means not pointing at more traditional targets that have better theoretical justification for potentially hosting detectable signals. If the observation turns up nothing, which is the expected outcome, that's telescope time spent with zero scientific return. Proposal reviewers are understandably reluctant to approve what looks like a long shot. But there's also a more subtle issue if you point a radio telescope at 3IATLAS and detect a signal. You've just created a massive problem. First contact protocols require verification, international coordination, careful analysis before public announcement. The discoverer becomes responsible for managing what could be the most consequential observation in human history. Most scientists prefer not to put themselves in that position, especially when the probability seems low. So we're left with a tantalizing connection that can't be confirmed or ruled out without observations. Nobody is conducting. The wow signal happened. 3IATLAS is arriving from approximately the same direction 48 years later. The math for a radar transmission from the object's 1977 position works out. The Doppler shift matches. The timing of active scanning versus arrival at inner system aligns with what you'd expect from a mission profile designed to explore a planetary system. But without new detections, it remains circumstantial, suggestive, but not conclusive. A pattern that could be meaningful or could be the kind of false pattern humans excel at finding in random data. We see faces in clouds. We see constellations in random star distributions. We see connections between events separated by decades because our brains are wired to find causation, even when only correlation exists. The scientific response is to gather more data, monitor 3IATLAS with radio telescopes, analyze its trajectory for any deviations that might indicate deliberate navigation toward Earth orbit or planetary encounters, look for secondary signals, transmissions, that might occur as it passes perihelion or approaches Earth in December. Document everything, and let the evidence accumulate until patterns either resolve into clear, natural explanations or into something that demands we reconsider what we think we're looking at. November and December will be critical for this as the object becomes easily observable again, post-perihelion. Any research group with access to radio telescope time could in principle conduct observations. Whether they will depends on funding, proposal approvals, and willingness to spend resources on what most consider a low probability target. But the window is limited. By February 3, IATLAS will be moving back into the outer solar system, fading from view, and the opportunity to test the wow signal hypothesis directly will be gone. If transmissions are detected, everything changes. The conversation shifts from whether 3IATLAS is unusual to what we do about confirmed intelligent technology operating in our solar system. If no transmissions are detected, the connection remains speculative, an interesting coincidence that generates papers and discussions but doesn't fundamentally alter our understanding. Either way, the wow signal reminds us that the universe has already handed us one unexplained event that looks tantalizingly like contact, 3IATLAS, arriving from the same direction decades later. Might be coincidence, or it might be the universe giving us a chance to connect the dots, to see a pattern that spans nearly 50 years and reveals something profound about our place in the cosmos. We just need to be willing to look. The 8 Loeb anomalies rank 4 on the scale. Loeb developed his scale for the interstellar object specifically because 3IATLAS demanded it. Before this object appeared, the framework didn't exist. There was no standardized way to quantify how unusual an interstellar visitor might be, no metric for assessing technological probability. Loeb created a 10-point scale where 0 represents definitely natural, 10 represents definitely artificial, and the middle ranges capture varying degrees of anomaly and uncertainty. 3IATLAS currently ranks at 4. That's not a guess or intuition. It's a calculation based on 8 specific anomalies, each of which has been assigned a probability of occurring naturally. Apply those probabilities together, and you get a cumulative likelihood that measures how expected or unexpected the object's characteristics are if it formed through natural processes. The result places it firmly in the uncertain zone, too strange to dismiss as ordinary but not definitely artificial. The first anomaly is trajectory alignment. 3IATLAS approaches the Sun on an orbital plane. It's inclined only 5 degrees from the ecliptic. The ecliptic isn't a physical structure. It's the plane defined by Earth's orbit and, by extension, the approximate plane where most solar system planets orbit. It exists because the solar system formed from a rotating disk of gas and dust, and conservation of angular momentum kept everything spinning in roughly the same plane. Interstellar objects have no connection to that plane. They form in other stellar systems with their own orientations. When they are projected into interstellar space, Their trajectories are randomized by gravitational interactions. Some go prograde, matching their parent system's rotation. Others go retrograde. Inclinations span the full range from 0 to 90 degrees, with no preference for any particular value. For 3IATLAS to arrive aligned within 5 degrees of our ecliptic by pure chance requires specific geometry of all possible approach vectors from interstellar space. Only about 2% align that closely. It's not impossible. 2 in 100. But it's the first statistical oddity if you're designing a mission to explore a planetary system efficiently. You choose a trajectory in the ecliptic plane, because reaching planets from there requires minimal fuel. Starting from high inclination forces expensive plane change maneuvers. The 5-degree alignment is optimal for access, suspicious for natural arrival. The second anomaly is timing for planetary encounters. 3IATLAS passes within tens of millions of kilometers of Mars in early October, Venus in early November, and Jupiter in March 2026. Close approaches to multiple planets during a single pass are rare. Most interstellar objects either miss everything or encounter one body. By chance, the probability of arriving at just the right time to pass near 3 major planets is about 0.005%. 5 in 100,000, again, not impossible, but combined with the trajectory alignment, you're now at 2 unusual conditions happening simultaneously. The product of 2% and 0.005% is 0.01%. 1 in 10,000. We're in lottery odds territory. And we've only covered 2 anomalies. The third anomaly is mass. 3IATLAS is enormous compared to the other interstellar visitor, Oumuamua. The first detected in 2017 and was maybe a few hundred meters across with mass estimated in tens of thousands of tons. 2IATLAS Borisov. The second visitor in 2019 was slightly larger but still measured in the low millions of tons. 3IATLAS, with a minimum diameter of 5 kilometers and mass exceeding 33 billion tons, outweighs both predecessors by factors of thousands to millions. It also moves faster. Oumuamua entered at about 26 kilometers per second hyperbolic excess velocity. Borisov came in at 32 kilometers per second. 3IATLAS arrives at 58 kilometers per second. Not only is it more massive, it's carrying more kinetic energy by huge margins. The combination of extreme mass and high velocity is uncommon. Most massive interstellar objects would be gravitationally bound to their parent stars. Only rare ejection events produce massive objects with high velocities. The probability of detecting one during the brief window when humanity has the technology to identify interstellar visitors is well below 1%. The fourth anomaly is composition, specifically the nickel emissions. The Keck Observatory's spectroscopic analysis in August showed prominent nickel emission lines without corresponding iron lines. That ratio is wrong for natural objects. Nickel and iron are sister elements, formed together in stellar nuclear synthesis, and found in similar ratios throughout the universe. Rocky bodies, asteroids, comets all show iron alongside nickel when you analyze their spectra. Industrially produced used nickel alloys on Earth deliberately concentrate nickel, while minimizing iron because of the alloy's useful properties. Stainless steel, superalloys for jet engines, corrosion-resistant materials all use high nickel, low iron compositions. Finding that signature in a comet is like finding refined aluminum in a meteorite. Technically possible if some exotic natural process creates extreme chemical fractionation, but so rare that the probability is below 1%. The fifth anomaly is water content. James Webb Space Telescope measurements showed 3IATLAS has only 4% water by mass in its outgassing. Most comets are primarily water ice, with smaller amounts of carbon dioxide, carbon monoxide, and other volatiles. Solar system comets typically show water accounting for 70 to 90% of outgassing. even accounting for compositional variations and formation environment differences. 4% is extraordinarily low. Carbon dioxide dominates instead, making up 87% of the observed volatiles. That inverted ratio suggests either the object formed in an extremely cold environment where carbon dioxide ice is more abundant than water ice, or the surface we're observing is depleted in water while retaining carbon dioxide. Both explanations work, but require specific conditions. The probability of encountering an interstellar comet with such unusual composition is difficult to quantify precisely, but likely under 5%. The sixth anomaly is polarization. The Very Large Telescope's observations in September showed extreme negative polarization, meaning light scattered from the coma had its wave orientation parallel to the scattering plane, rather than perpendicular. This behavior is almost unprecedented in comets. The dust particle size distributions and compositions required to produce it are very specific. Natural comet dust tends to have wide size ranges and mixed composition, producing positive polarization in most cases. Laboratory experiments can create negative polarization with carefully controlled particle sizes, usually in the micrometer to submicrometer range, and specific refractive indices. Finding those exact conditions in a natural comet coma, where dust is continuously being produced and ejected in varying sizes, is extremely unlikely. The VLT team assessed probability at below 1%. The seventh anomaly is the lack of non-gravitational acceleration. Despite visible outgassing, Richard Cluett, Peter Verrees, and Avi Loeb analyzed over 4,000 positional measurements from 227 observatories worldwide, spanning from mid-May through late September. They found no detectable deviation from purely gravitational motion. The residuals in right ascension and declination were consistent with zero. That sounds like it should be normal. Gravity governs orbital motion. But for active comets, it's not normal. When comets outgas, the vapor jets create recoil forces that push the nucleus slightly off its gravitational trajectory. These non-gravitational accelerations are well documented and routinely measured for solar system comets. The magnitude depends on the comet's mass and the strength of outgassing. Small active comets show large deviations. Large comets show smaller but still detectable deviations. 3IATLAS is outgassing vigorously, losing 25 kilograms per second according to Webb observations. That should produce measurable recoil. The fact that no deviation was detected means either the outgassing is perfectly symmetric so forces cancel out, or the object's mass is so large that the recoil is below detection threshold. Perfectly symmetric outgassing is inconsistent with the observed anti-tail and geometric plasma patterns, which indicate asymmetry. So the object must be extremely massive. Working backward from the detection limits, the analysis concluded 3IATLAS must be at least 33 billion tons. That's about 1,000 times more massive than 2I Borisov, despite being only a few times larger in diameter. The implied density is much higher than typical comets, which are loosely bound rubble piles with lots of empty space. High density suggests either the object is primarily rock, rather than ice, or it has internal structure that's not porous like typical comets. The eighth anomaly loops back to the WOW signal alignment. 9 degrees directional match with 0.6% random probability. On its own, this is the weakest anomaly. 9 degrees is a large uncertainty cone in interstellar space, but in the context of the other 7, it adds another layer of statistical improbability. Multiply all 8 probabilities together. 2% for trajectory alignment, 0.005% for planetary encounter timing, below 0.1% for the mass and velocity combination, below 1% for the nickel-iron ratio, under 5% for the low water composition, below 1% for the extreme polarization, below 1% for the extreme density implied by lack of non-gravitational acceleration, and 0.6% for wow signal alignment. The cumulative probability is absurdly small, parts per quadrillion. Loeb and his colleagues calculated the exact ACT value at less than 1 in 10 to the 16th power. That's 1 in 10 quadrillion. To put it differently, if you observe 10 quadrillion random interstellar objects, you'd expect to see one with this combination of characteristics purely by chance. Now, there's a statistical trap here. After the fact, you can make anything look improbable if you carefully select which characteristics to measure and which probabilities to multiply. You can create seemingly impossible odds for any object. This is called the Texas sharpshooter fallacy, where you shoot bullets into a barn wall and then draw targets around the holes to make it look like you hit bullseyes. The counter to that fallacy is to define your criteria in advance and apply them consistently. Loeb scale attempts to do that. The 8 anomalies weren't cherry-picked after discovering they were unusual. They're the kind of parameters you'd naturally examine for any interstellar visitor. Trajectory, mass, composition, behavior. These are fundamental observables. The fact that all of them happen to be in the unusual tail of their probability distributions isn't a case of selecting convenient facts. It's the object itself being consistently weird across independent measurements. That's why 3IATLAS ranks at 4 on the scale. It's not one bizarre characteristic that might be a fluke. It's 8 independent characteristics, all pushing toward the low probability end. Natural explanations exist for each one individually, but explaining all of them simultaneously requires compounding multiple rare conditions, which becomes less parsimonious than considering a single alternative explanation. The alternative is that 3IATLAS is artificial, a probe, spacecraft, or other technological construct sent from another stellar system to explore ours. If that's true, all 8 anomalies resolve into expected features. The trajectory alignment is deliberate navigation. The planetary encounter timing is mission planning. The extreme mass and velocity are propulsion system capabilities. The nickel-iron ratio is materials engineering. The low water content is a thin surface layer mimicking comet activity while protecting underlying systems. The extreme polarization is surface coating properties. The lack of non-gravitational acceleration is structural integrity of a solid, manufactured object. The WOW signal alignment is the transmission location from 48 years ago. During Approach 1, hypothesis, 8 predictions confirmed. That's how Occam's razor is supposed to work. The simplest explanation, meaning the one with fewest independent assumptions, is preferred. 8 separate, unusual natural conditions versus 1 exotic artificial origin. The artificial hypothesis is simpler in that sense, even though it sounds more extraordinary. But extraordinary claims require extraordinary evidence. Statistical anomalies, however improbable, aren't the same as physical proof. We need observations that can't be explained naturally, even in principle. Radio transmission. Resolved surface structures showing manufactured features. Trajectory changes that can't result from outgassing or radiation pressure. Active deployment of secondary objects. Something definitive that breaks the ambiguity. Ranking at 4 means uncertain. Could be natural. Could be artificial. The data doesn't force a conclusion either way. If post-perihelion observations show continued natural comet behavior, the ranking drops to 2, meaning unusual but probably natural. If observations show impossible natural behavior, controlled maneuvers, obvious technological signatures, the ranking rises toward 10. We're in the middle, suspended between mundane and profound explanations. The 8 anomalies of C2023A3 are noteworthy, whether it's noteworthy as the weirdest comet we've ever seen, or noteworthy as first contact with extraterrestrial technology, depends on data we don't have yet. December's observations will push the ranking one direction or the other. Until then, rank 4 is where it sits, a number that says we genuinely don't know what we're looking at. And that uncertainty matters. The prophet and the mothership, Brandon Biggs didn't set out to become known as the prophet who predicted the Trump assassination attempt. But in April 2020, 4 months before the July 13th shooting at a Pennsylvania rally, Biggs recorded a video describing a vision. He spoke about seeing a bullet fly past Donald Trump's ear, so close it burst his eardrum. He described the chaos, the blood, Trump surviving but injured, when the actual attempt happened in July, matching those details with eerie precision. Biggs went from obscure Christian pastor to viral phenomenon overnight. That track record, that one incredibly specific prediction that came true, gives his subsequent visions a weight they might not otherwise carry. When someone calls something that unlikely, that detailed, you pay attention to what they say next, even if you're skeptical of prophetic claims in general. What Biggs said next in a video released in mid-October was about aliens, specifically about a giant mothership arriving on Earth. In his vision, Biggs described seeing a massive alien craft flying over the Vatican and Mayan temples in Mexico. Not two ships, one. He emphasizes that detail. He asked in the vision whether there were multiple craft and was told no, just one enormous vessel. The ship moves slowly across the ocean in full view. Everyone sees it. It is broadcast on television worldwide, creating global panic. Then, smaller craft to emerge from the mothership. Biggs describes them as balls of light, mini ships that scatter from the primary vessel. The timing of this video, released in mid-October as 3IATLAS approached perihelion, triggered immediate speculation online. Social media exploded with theories, connecting Biggs's vision to the interstellar object. Forums lit up with discussions, comparing his description of a mothership releasing smaller probes to Avi Loeb's hypothesis about 3IATLAS potentially deploying mini spacecraft at perihelion. The parallels are striking. Biggs talks about one large vessel releasing multiple smaller objects. Loeb talks about a mothership scenario where 3IATLAS, if artificial, would release mini-probes during its closest approach to the Sun. Biggs had actually mentioned this vision earlier, back in July, shortly after 3IATLAS was discovered. He described seeing little ships coming out of a larger craft, balls of light emerging from something massive. At the time, most viewers interpreted it as generic prophetic imagery, the kind of vague apocalyptic scenario common in religious visions. But the July timing, right when 3IATLAS entered public consciousness, and the October emphasis right before perihelion, created a narrative arc that conspiracy communities found impossible to ignore. The theological framework Biggs uses is important context. He's not claiming these are benevolent extraterrestrial visitors. He frames them explicitly as demonic entities, spiritual forces using physical manifestation to deceive humanity. In his interpretation, the mothership and the smaller craft are a satanic deception, part of a larger end-time scenario preparing the world to accept the Antichrist. The beings aren't aliens in the science fiction sense. They're fallen angels or demons, taking forms that modern secular society will interpret as extraterrestrial. This theological lens doesn't make his predictions less interesting from a phenomenological standpoint. If you strip away the spiritual interpretation and look at just the claimed observations, flying objects, mothership releasing smaller craft, global visibility, television coverage, you're left with descriptions that could apply to physical phenomena, regardless of their ultimate nature or origin, whether you interpret those phenomena as technology from another stellar system or manifestations of spiritual entities becomes a matter of worldview. The internet did what the internet does. Within hours of Biggs's October video circulating, edited versions appeared linking his statements directly to 3IATLAS. Some added images of the object from Hubble and JWST. Others overlaid orbital diagrams showing its trajectory. The synthesis created a narrative where a Christian prophet and a Harvard astrophysicist were independently describing the same event from different conceptual frameworks. Loeb talks about Oberth maneuvers and mini-probe deployment. Biggs talks about motherships and balls of light. The vocabulary differs, but the core scenario aligns. Mainstream media largely ignored this connection. Prophetic visions don't make comfortable material for science journalism, but alternative media, conspiracy-focused platforms, and religious communities amplified it aggressively. For certain audiences, the combination of Biggs' credibility from the Trump prediction plus the scientific anomalies surrounding 3IATLAS created a perfect storm of validation. Here was a spiritual warning confirmed by empirical observation or, depending on your perspective. Here was interesting astronomical data being wrapped in apocalyptic religious interpretation. The balls of light detail is particularly interesting because it echoes descriptions from UAP encounters, unidentified aerial phenomena reports, especially from military personnel, frequently describe luminous spheres that move in ways inconsistent with known aircraft. These aren't necessarily connected to 3IATLAS, but the descriptive overlap between Biggs's vision and existing UAP reports added another layer of cross-validation for those predisposed to see connections. Skeptics point out that prophetic visions are inherently unfalsifiable until they either happen or don't. Biggs can describe anything, and if it doesn't occur, supporters will argue the timeline was misinterpreted or the prediction was conditional on human response. If something vaguely matching the description happens, it gets counted as a hit. Even if details are loose, the Trump assassination prediction is the exception, specific enough and accurate enough that explaining it away requires uncomfortable contortions. But one accurate prediction doesn't validate all subsequent claims. There's also the problem of influence. Biggs has access to the internet. He follows news. By October 3, IATLAS was headline material. Loeb's mothership hypothesis had been discussed in major publications. Could Biggs have absorbed that information consciously or unconsciously and incorporated it into his religious framework? Vision and imagination are hard to distinguish, especially when both draw from the same informational environment. Claiming divine revelation about something you've read about, even if you don't consciously remember. Reading it is a well-documented psychological phenomenon. But then there's the July mention Biggs described ships and balls of light. Back when 3IATLAS was barely known outside specialist circles, Loeb hadn't yet published detailed papers on the technological hypothesis. The mothership scenario wasn't mainstream discussion. If Biggs was unconsciously pulling from media coverage, what coverage existed in early July that would have planted those specific images? The object had just been discovered. Initial reports called it a comet. Interesting because it was interstellar but not yet laden with anomaly discussions or technological speculation. That timing issue is why some take Biggs more seriously than they otherwise might. Either he got very lucky guessing that an interstellar object would become associated with mothership theories, or he had genuine insight through whatever process produces his vision, psychological, spiritual, or otherwise. The Trump prediction makes lucky guessing harder to accept as explanation. From a sociological perspective, Biggs represents something important. Regardless of prophetic accuracy, he's a conduit through which scientific uncertainties get translated into religious narrative. 3IATLAS, with its statistical anomalies and technological hypothesis, creates space for apocalyptic interpretation. People looking for signs of end times see a mysterious object from the stars. Possibly releasing probes into our solar system is exactly the kind of event that would precede major prophetic fulfillments. The beast system, one world government, the revealing of hidden truths. All classic eschatological themes find purchase in interstellar visitor scenarios. This isn't new. Every major astronomical event in history gets interpreted through religious frameworks. Comets were omens in ancient times. Eclipses signaled divine displeasure. Modern UFO phenomena get absorbed into both secular and religious explanatory systems. 3IATLAS is just the latest celestial occurrence being pulled into those interpretive structures, amplified by social media, and the genuine scientific puzzles the object presents. What makes this case unusual is the convergence. You have a prophet with demonstrated credibility from a recent, specific prediction. You have a scientific hypothesis from a respected astrophysicist that uses mothership language. You have timing synchronicity where the vision details align with a perihelion window, when deployment would theoretically occur, and you have an object that's genuinely anomalous, enough that even skeptical scientists admit it's worth serious attention. That convergence doesn't prove anything about prophecy, or alien visitation, or spiritual manifestation. It proves that when reality gets weird enough, multiple explanatory frameworks start pointing at the same phenomena. Scientists say probe deployment. Prophets say demonic manifestation. Both could be wrong. Both could be partially right in ways that don't contradict each other. An advanced civilization's technology would look like magic to less advanced observers. Clarke's third law. Sufficiently advanced technology is indistinguishable from supernatural phenomena. If 3IATLAS does release objects at perihelion, if we see secondary spacecraft emerging from the primary body, how will different communities interpret that scientists will analyze trajectories, spectrometry, propulsion signatures? They'll try to determine origin, purpose, capabilities. Religious communities will see fulfillment of prophecy, evidence of spiritual warfare, signs of approaching end times. Both interpretations will be internally consistent within their frameworks. Both will feel validated by the observations. This is where epistemology matters. How do we know what we know? Science relies on observation, measurement, repeatability. Religion relies on revelation, scripture, spiritual discernment. When both point at the same event and say something significant is happening, but describe it in incompatible vocabularies, resolution becomes difficult. You can't prove spiritual entities aren't using physical craft to manifest. You can't prove advanced aliens aren't being misinterpreted as angels or demons. The frameworks are incommensurable in important ways. What we can say is Biggs described a scenario using language from his religious tradition that overlaps significantly with scenarios described by scientists using secular language. Whether that overlap results from shared underlying reality, from influence and information contamination, or from pure coincidence, doesn't change the sociological impact. Millions of people across religious and secular communities are now watching 3IATLAS with heightened attention, expecting something dramatic. That expectation matters if nothing unusual happens. If the object completes its perihelion passage and continues on a purely gravitational trajectory, showing normal cometary evolution, both communities will experience disappointment. Scientists who allowed themselves to consider the technological hypothesis will return to conventional explanations. Religious communities will adjust prophetic timelines, or reinterpret the vision as symbolic rather than literal. Life continues. But if something does happen, if we observe deployments, maneuvers, transmissions, anything that confirms the mothership scenario, in scientific terms, the religious interpretation gains immense cultural power. Biggs will have predicted not just one unlikely event, but two: the Trump assassination and the alien arrival. That track record would make him one of the most credible prophetic voices in modern history. Whether you accept his theological framework or not,